On a frigid morning in January 2023, researchers at the Space Telescope Science Institute in Baltimore encountered data that prompted immediate verification of their instrumentation. Observations from the James Webb Space Telescope, the most sensitive and powerful observatory ever deployed, revealed an anomalous signal emanating from a region of space traditionally considered void. The signal exhibited unexpected characteristics. Its wavelength did not correspond to any known astrophysical source. Its intensity was inconsistent with established emission models, and its temporal pattern defied all conventional predictions. Initial analyses ruled out instrumental artifacts, data corruption, and known cosmic phenomena. The signal's origin and properties challenge fundamental assumptions about the structure and behavior of the universe. Scientists across multiple disciplines are now investigating potential explanations, from exotic astrophysical processes to previously unconsidered interactions in the fabric of space-time. If confirmed, this anomaly may necessitate a profound re-evaluation of physical laws that have remained unchallenged for over a century, opening the door to new paradigms in cosmology and fundamental physics. The telescope that changed everything. The James Webb Space Telescope didn't just appear overnight. It took 3 decades of planning, $10 billion, and the combined efforts of NASA, the European Space Agency, and the Canadian Space Agency to make it real. Launched on Christmas Day 2021, Webb was designed to be the successor to Hubble, but calling it an upgrade doesn't do it justice. Webb is not just bigger or more powerful. It represents a completely different way of seeing the universe, tuned to wavelengths of light that reveal things Hubble could never detect. The key difference is infrared. While Hubble primarily observes visible light, the kind our eyes can see, Webb specializes in infrared radiation. This might sound like a technical detail, but it changes everything. Infrared light has longer wavelengths than visible light, which means it can penetrate dust clouds that block optical telescopes. It can also detect objects that are extremely cold or extremely far away, because the expansion of the universe stretches light from distant sources into the infrared spectrum, a phenomenon called redshift. This makes Webb perfectly suited for looking back in time, observing the first galaxies that formed just a few 100 million years after the Big Bang. Webb's primary mirror is massive, measuring 6.5 meters across compared to Hubble's 2.4 meters, but it's not a single piece of glass. It's composed of 18 hexagonal segments made of beryllium and coated with a microscopically thin layer of gold. Gold reflects infrared light better than any other material, making it ideal for Webb's mission. These segments fold up to fit inside the rocket during launch, then unfold in space like a giant origami flower. Each segment can be individually adjusted with nanometer precision, allowing the telescope to focus with unprecedented clarity. The telescope doesn't orbit Earth like Hubble does. Instead, it sits at a point called L2, the second Lagrange point, about 1.5 million kilometers from Earth, in the direction opposite the Sun. At this location, the gravitational pulls of the Earth and Sun balance out, allowing Webb to maintain a stable position with minimal fuel. But there's another crucial advantage. At L2, Earth, Sun, and Moon are all in the same direction, which means Webb can deploy a massive sunshield to block their heat and light simultaneously. This sunshield is the size of a tennis court and keeps the telescope at temperatures around minus 230 degrees Celsius, cold enough for its sensitive infrared instruments to operate without interference from heat. The instruments themselves are marvels of engineering. The near-infrared camera, or NIRCam, is Webb's primary imager, capable of detecting light from the first stars and galaxies. The near-infrared spectrograph, NIRSpec, can split light into its component wavelengths, revealing the chemical composition, temperature, and motion of distant objects. The mid-infrared instrument, MIRI, operates at even longer wavelengths and includes both a camera and a spectrograph. And the fine guidance sensor, combined with the near-infrared imager and slitless spectrograph, helps Webb lock onto targets with extraordinary precision while also conducting its own science observations. What makes Webb truly revolutionary is its ability to observe things that are not just far away, but fundamentally invisible to other telescopes. It can see through the dust clouds where stars are born. It can detect the atmospheres of exoplanets, searching for chemical signatures that might indicate life. It can peer into the hearts of distant galaxies to study the supermassive black holes that anchor them. And it can look back to the cosmic dark ages, the period before the first stars ignited, searching for clues about how the universe transitioned from a hot, uniform soup of particles to the rich tapestry of structures we see today. Since it began operations, Webb has exceeded every expectation. It captured images of galaxies so distant that their light has been traveling toward us for over 13 billion years, meaning we're seeing them as they appeared when the universe was less than 700 million years old. It discovered organic molecules in the atmosphere of an exoplanet 700 light-years away. It revealed the detailed structure of the pillars of creation with clarity that made Hubble's famous image look blurry by comparison. It found evidence of water vapor in the atmosphere of a rocky planet, detected complex carbon compounds in distant nebulae, and mapped the weather patterns on Jupiter with stunning detail. But nothing Webb has discovered so far compares to what happened in January 2023. The telescope was conducting a deep field observation, staring at a patch of apparently empty sky for days to collect as much light as possible from the faintest, most distant objects. This is standard procedure. By pointing at darkness and waiting, astronomers can detect galaxies and structures that are otherwise invisible. The data was being processed in stages, with preliminary results reviewed by the science team to check for any issues or interesting targets. That's when they saw it. Buried in the infrared spectrum, coming from a region that should contain nothing but intergalactic void, was a signal. Not random noise, not a cosmic ray hit on the detector, but a clear structured pattern of emission at specific wavelengths. The team ran diagnostics on the instruments. Everything checked out. They compared the signal to known sources, stars, galaxies, nebulae, quasars. Nothing matched. They looked for artifacts, reflections from nearby bright objects, scattered light, electronic interference. The signal remained. What made it truly strange was the combination of properties. The wavelength suggested the source was extremely cold, far colder than the cosmic microwave background radiation that fills all of space. But the intensity indicated something was actively emitting energy, not just reflecting it. The spectrum showed absorption lines that didn't correspond to any known element or molecule. And perhaps most disturbing, the signal's redshift placed it at a distance where the universe was so young that according to current models, whatever is producing this signal shouldn't have had time to form. The discovery was kept quiet initially. In astronomy, extraordinary claims require extraordinary evidence, and the team needed to be absolutely certain before announcing anything. They requested additional observation time, pointing Webb back at the same region from different angles and at different times. The signal persisted. They compared it with data from other telescopes, including radio observations, X-ray satellites, and ground-based infrared instruments. None of them saw anything in that location. The signal was only visible to Webb, only in specific infrared wavelengths, and only when observed with sufficient sensitivity and exposure time. As word spread through the astronomical community, the speculation began. Some suggested it could be a previously unknown type of galaxy, one formed from exotic matter or under conditions we don't understand. Others proposed it might be a gravitational lensing effect, where light from a background object is bent and amplified by an invisible mass in the foreground. A few even wondered if it could be evidence of physics beyond the standard model, particles or forces that interact with light in ways we've never observed. But there was another possibility, one that nobody wanted to say out loud, but everyone was thinking. What if the signal was artificial? What if Webb had detected not a natural phenomenon, but a transmission from an intelligence far older and more advanced than anything we could imagine? The implications were staggering, and the burden of proof was enormous. The James Webb Space Telescope had changed everything about how we observe the universe. Now it might be forcing us to change everything about how we understand our place within it. The signal that defied physics. When astronomers describe something as impossible, they usually mean unlikely or unexpected. But the signal Webb detected was impossible in a more fundamental sense. It violated basic principles that govern how matter and energy behave in our universe. To understand why this was so troubling, we need to understand what the signal actually showed, and why every conventional explanation failed. The first anomaly was the temperature. Every object in the universe emits thermal radiation based on its temperature, a relationship described by Planck's law and Wien's displacement law. Hotter objects emit more energetic photons with shorter wavelengths, which is why heated metal glows red, then orange, then white as it gets hotter. Colder objects emit at longer wavelengths. The cosmic microwave background, the leftover radiation from the Big Bang, has a temperature of 2.7 Kelvin and emits primarily in microwave wavelengths. The signal Webb detected had a spectrum consistent with something even colder, around 1.5 Kelvin, well below the temperature of empty space. This shouldn't be possible. The cosmic microwave background permeates all of space, constantly bathing every object in its gentle warmth. Nothing in the universe can be colder than this background radiation unless it's actively being cooled, which requires energy and sophisticated mechanisms. In deep space, with no stars nearby and no obvious source of cooling, finding something colder than the CMB is like finding ice in a furnace. It defies thermodynamics. But the signal wasn't just cold, it was also bright, at least in the specific wavelengths where it appeared. This created a paradox. Cold objects are dim because they emit very little energy. A cold gas cloud might emit faintly in radio waves. A cold dust cloud might emit weakly in far infrared. But this signal had intensity levels suggesting significant energy output, which should make it hot, not cold. It was as if Webb had found a flashlight that shone brightly while remaining frozen solid. The spectral lines made things even stranger. When light passes through gas, atoms absorb specific wavelengths corresponding to their electronic structure, creating dark absorption lines in the spectrum. When gas emits light, it produces bright emission lines at those same wavelengths. These spectral fingerprints allow astronomers to identify the chemical composition of distant objects: hydrogen, helium, carbon, oxygen, iron. Every element has a unique pattern. The signal showed absorption lines, lots of them, but they didn't match any known element. The spacing between the lines didn't correspond to hydrogen or helium, the most common elements in the universe. It didn't match carbon, nitrogen, oxygen, or any of the heavier elements forged in stars. Researchers compared the pattern to exotic molecules, complex organic compounds, even theoretical forms of matter like strange quarks or supersymmetric particles. Nothing fit. One possibility was that the lines belonged to known elements but were shifted by some extreme physical condition. In strong gravitational fields, light is redshifted by general relativity. In rapidly moving objects, Doppler shift changes the observed wavelength. In dense plasmas, spectral lines can be broadened and shifted by collisions and electric fields. But when astronomers tried to account for these effects, they couldn't make the observed pattern match any combination of known chemistry. The signal's location added another layer of mystery. Based on its redshift, the source appeared to be about 13.2 billion light-years away, meaning we were seeing it as it existed just 600 million years after the Big Bang. This is the epoch when the first galaxies were forming, when the universe was transitioning from darkness to light as the first stars ignited. It's a crucial period in cosmic history, and Webb was specifically designed to study it. But the signal didn't resemble any early galaxy. Young galaxies should be hot and bright, full of massive stars pumping out ultraviolet radiation. Even if dust absorbed that UV light and re-radiated it in the infrared, the spectrum would show clear signs of stellar activity, emission from ionized gas, absorption from heavy elements synthesized in supernovae. This signal had none of that. It was cold, chemically bizarre, and sitting in an era when such an object should not exist. Researchers considered whether it could be a primordial gas cloud that had somehow avoided forming stars. In the early universe, there were vast reservoirs of hydrogen and helium left over from the Big Bang. Most of this gas eventually collapsed under gravity to form the first stars and galaxies, but perhaps some pockets remained undisturbed. If such a cloud existed, it would be cold and would emit faintly in the infrared. But it should emit at wavelengths corresponding to hydrogen, not the unidentified lines Webb observed, and it should be even dimmer than the cosmic microwave background, not brighter. Another hypothesis was gravitational lensing. Sometimes a massive object like a galaxy or cluster sits between us and a more distant source, bending the light like a cosmic magnifying glass. This can make faint background objects appear brighter and can create multiple images or distorted arcs. Perhaps the signal was a background source being amplified by a foreground lens. But surveys of the region showed no massive structures that could act as a lens, and lensing preserves the spectrum of the source. It makes things brighter, but doesn't change their color or spectral features. The mysterious absorption lines would still need an explanation. Some scientists proposed exotic physics. Perhaps the signal came from a region where dark matter was concentrated enough to interact with normal matter in unusual ways. Dark matter is invisible and doesn't emit light, but it has gravity, and in principle, it could affect how normal matter behaves. If a dense clump of dark matter existed in that region, it might alter the temperature or spectrum of any gas passing through it. But there's no evidence that dark matter has such effects, and proposing new physics to explain one observation is a last resort, not a first response. Others suggested the signal might be related to the cosmic web, the large-scale structure of matter in the universe. Galaxies aren't distributed randomly. They cluster along filaments of dark matter and gas, creating a web-like pattern. Where these filaments intersect, matter can pile up and heat up due to gravitational collapse, creating regions that emit X-rays. Perhaps Webb had detected a cold filament, a stream of gas connecting galaxies. But again, the spectrum didn't match. Filaments should show hydrogen emission, not mysterious absorption lines. As explanations were proposed and discarded, frustration grew. Every conventional idea failed. Every exotic idea lacked supporting evidence. The signal remained stubbornly anomalous, refusing to fit into any box. And then someone asked the question that had been lurking unspoken in every meeting and every email. What if the signal wasn't natural at all? The idea seemed absurd. Astronomers had spent decades searching for signs of extraterrestrial intelligence, pointing radio telescopes at nearby stars, and listening for signals that might indicate technology. The search for extraterrestrial intelligence, or SETI, had detected plenty of interesting signals over the years, but all of them turned out to be either natural phenomena or human-made interference. The famous WOW signal from 1977 remains unexplained, but is widely believed to be either a rare astronomical event or a reflection of Earth-based transmission. But this was different. The signal wasn't a radio transmission from a nearby star. It was infrared emission from the early universe, from a time when Earth didn't exist, when the Sun hadn't formed, when the Milky Way was still assembling itself from smaller galaxies. If it was artificial, it implied a civilization that existed when the universe was less than 5% of its current age. A civilization advanced enough to leave a mark visible across billions of light years and billions of years. The notion was almost too big to contemplate. But as every natural explanation failed, the unthinkable started to seem less impossible. The signal defied physics. It came from the wrong place at the wrong time with the wrong properties. And the one thing nobody could explain was why it existed at all. Cosmic microwave background and the temperature problem. To understand why the signal's temperature was so problematic, we need to understand one of the most important discoveries in cosmology, the cosmic microwave background radiation. This faint glow fills the entire universe, a relic from the moment when atoms first formed, and light could travel freely through space. It's the afterglow of the Big Bang, and it sets a fundamental limit on how cold anything in the universe can be. The story begins about 380,000 years after the Big Bang. Before this time, the universe was a hot, dense plasma of protons, electrons, and photons. The photons were constantly scattering off the charged particles, unable to travel any significant distance. It's like being in a thick fog where light bounces from water droplet to water droplet, never going far. But as the universe expanded, it cooled. Eventually, it reached a temperature where electrons and protons could combine to form neutral hydrogen atoms. This process is called recombination. Once atoms formed, photons were no longer scattered by free electrons. They could travel unimpeded across the universe. The light from this moment has been traveling through space ever since, stretched by cosmic expansion from visible wavelengths into microwaves. Today, we detect it as a nearly uniform glow with a temperature of 2.725 Kelvin, just a few degrees above absolute zero. This is the cosmic microwave background, or CMB. The CMB is everywhere. No matter which direction you look in space, you detect this radiation. It's one of the strongest pieces of evidence for the Big Bang theory and provides a wealth of information about the early universe. By measuring tiny variations in the CMB temperature across the sky, astronomers can learn about the density of matter in the early universe, the expansion rate, and the initial conditions that led to the formation of galaxies and clusters. But for our purposes, the most important property of the CMB is that it sets a minimum temperature for everything in the universe. Any object sitting in space is bathed in this radiation and will absorb it, heating up until it reaches thermal equilibrium with the CMB. You can't make something colder without actively removing energy, which requires work and sophisticated mechanisms like refrigerators or lasers. On Earth, we can cool things below the CMB temperature because we have technology. Laboratories routinely create conditions colder than outer space using liquid helium, magnetic cooling, or laser trapping of atoms. But these processes require energy input and complex equipment. In deep space, with no stars nearby and no obvious machinery, finding something colder than 2.7 Kelvin is extraordinarily difficult. There are a few natural exceptions. Certain gas clouds expanding rapidly can cool through a process called adiabatic expansion, where the gas does work against its own pressure and loses thermal energy in the process. The Boomerang Nebula, a cloud of gas expelled from a dying star, has regions as cold as 1 Kelvin because it's expanding so quickly. But even this requires a specific set of conditions: a central star providing energy to drive the expansion, and a dense enough gas that it can cool efficiently. The signal Webb detected had a spectral profile consistent with 1.5 Kelvin, colder than the CMB. If it was real and not an artifact, then something in that region of space was either naturally cooling itself through some process we don't understand, or it was being artificially cooled by technology. Neither option fit comfortably into established science. Researchers tried to model scenarios where natural cooling could occur. One idea was that the signal came from a cloud of molecular gas undergoing rapid expansion. Molecular clouds can cool efficiently because molecules have many energy states that can be excited and then radiate away energy. If a cloud was being pushed outward by some force, perhaps a nearby supernova or a burst of radiation from a quasar, it might cool below the CMB temperature temporarily. But this model had problems. First, molecular clouds in the early universe were rare. The chemistry needed to form molecules like carbon monoxide or water requires heavier elements forged in stars, and 600 million years after the Big Bang, there hadn't been enough time for many stellar generations to enrich the gas with these elements. Second, even if such a cloud existed, it should show spectral lines from known molecules, not the mysterious absorption features Webb observed. Third, the cooling would be temporary. Once the expansion stopped, the cloud would reabsorb CMB photons and warm back up. Another possibility was evaporative cooling, the same process that makes sweat cool your skin. If a gas cloud had a mix of temperatures, the hottest particles could escape, leaving behind the cooler ones. Over time, this would reduce the average temperature of the cloud. But again, this required specific conditions that didn't seem to match the observations, and it still wouldn't explain the bizarre spectrum. Some researchers proposed that the signal might be related to dark matter. If dark matter particles could decay or annihilate, they might produce photons with specific wavelengths. If this process occurred in a cold dark matter halo, the resulting radiation could have unusual properties. But dark matter interactions with normal matter are extraordinarily weak, and no proposed dark matter candidate produces the observed spectrum. Moreover, dark matter alone wouldn't explain why the source appeared colder than the CMB. The temperature anomaly became even more puzzling when combined with the signal's brightness. In thermodynamics, there's a relationship between temperature and luminosity. Hotter objects emit more energy per unit area, which is why the sun is bright and a cold asteroid is dim. The signal had the spectrum of something very cold, but the intensity of something actively radiating. This combination violated the basic physics of blackbody radiation. One exotic proposal involved something called negative temperature. In certain quantum systems with a bounded energy spectrum, it's possible to create a state where the population of high-energy states is greater than the population of low-energy states. This inverted population is described by a negative temperature, not because the system is below absolute zero, but because the mathematical definition of temperature involves the change in entropy with energy, and this can be negative under specific conditions. Negative temperature systems are hotter than any positive temperature system. They emit energy more readily. They've been created in laboratories using lasers and magnetic fields to manipulate atoms, but they require precise control and exist only for fractions of a second. The idea that such a state could exist naturally in deep space and persist long enough to be detected seemed far-fetched. And even if it could, it still wouldn't explain the unidentified spectral lines. As researchers grappled with the temperature problem, they kept coming back to the same uncomfortable conclusion. If the signal was real, if it truly represented something colder than the cosmic microwave background while also emitting significant energy, then either our understanding of thermodynamics was incomplete, or something or someone was actively maintaining that temperature using methods beyond our current knowledge. Neither option was easy to accept, but the data wasn't going away. Spectroscopy and the chemical mystery. Spectroscopy is the art of splitting light into its component wavelengths and reading the information encoded in those colors. It's one of the most powerful tools in astronomy, allowing us to determine not just how bright or far away an object is, but what it's made of, how hot it is, how fast it's moving, and even what physical processes are occurring within it. Every element and molecule leaves a unique fingerprint in the spectrum of light it emits or absorbs. When the signal from Webb was run through spectroscopic analysis, it revealed a pattern that shouldn't exist. The process works like this. When atoms absorb light, electrons jump from lower energy levels to higher ones. The energy difference between these levels corresponds to specific wavelengths of light. Hydrogen, for example, has a series of absorption lines in the visible and ultraviolet spectrum called the Balmer series, Lyman series, and others. When we see these patterns in the light from a star or galaxy, we know hydrogen is present. Helium has its own pattern, as does carbon, oxygen, and every other element. Even molecules have characteristic spectra, though they're more complex because molecules can rotate and vibrate in addition to their electronic transitions. When astronomers analyzed Webb's signal, they found dozens of absorption lines, dark bands where specific wavelengths were missing. This was expected. Any cloud of gas will absorb light at characteristic wavelengths, but when they tried to match these lines to known elements, nothing worked. The pattern didn't correspond to hydrogen, the most abundant element in the universe. It didn't match helium, carbon, nitrogen, oxygen, or any combination thereof. They checked against databases containing thousands of spectral lines from every element and hundreds of molecules. No match. The first thought was redshift. Light from distant objects is stretched by the expansion of the universe, shifting spectral lines toward longer wavelengths. If the source was moving away from us, or if it was at a cosmological distance, its spectrum would be redshifted. Astronomers are used to this. They routinely measure the redshift of galaxies to determine their distance and look back time. You take the observed wavelengths, divide by 1 plus the redshift factor, and you get the rest frame wavelengths, the wavelengths that would be measured if you were sitting next to the source. The team calculated the redshift of the signal based on its expected distance and applied the correction. The corrected spectrum still didn't match anything. They tried different redshift values, thinking maybe their distance estimate was wrong. At every redshift they tested, the pattern remained unidentifiable. It was as if the source was made of elements that don't exist in our periodic table. This led some researchers to wonder if the signal could involve exotic matter. In particle physics, there are hypothetical forms of matter that have never been observed but are predicted by various theories. Supersymmetry predicts superpartners for every known particle, like selectrons and squarks. String theory allows for extra dimensions and exotic particles living in those dimensions. Some quantum gravity theories propose that particles might have internal structure at the Planck scale, much smaller than anything we can currently probe. If such particles existed in the early universe, before stars formed and the chemistry we know today was established, they might produce spectral lines at unfamiliar wavelengths. The problem is that these particles, if they exist, are expected to be extremely unstable or interact so weakly with normal matter that they wouldn't leave detectable spectral features. None of the proposed exotic particles have properties that match the observed spectrum. Another hypothesis involved isotopes. Most elements have several isotopes, atoms with the same number of protons, but different numbers of neutrons. Hydrogen has protium, deuterium, and tritium. Carbon has carbon-12, carbon-13, and carbon-14. Isotopes have slightly different masses, which means their spectral lines are shifted by tiny amounts compared to the most common isotope. In most astrophysical situations, these shifts are negligible, but in principle, a gas cloud with an unusual isotopic composition might produce a spectrum that looks unfamiliar. Researchers modeled clouds with extreme isotopic ratios, imagining scenarios where nearly all the hydrogen was deuterium, or where carbon-13 dominated over carbon-12. These models produced spectra that were shifted relative to normal, but they still didn't match the Webb signal. Moreover, there's no known process that would create such extreme isotopic enrichment in the early universe. Isotopes are produced in specific ratios by nucleosynthesis in stars and supernovae, and deviating significantly from those ratios requires conditions that don't exist in nature. Then there was the possibility of highly ionized atoms. When an atom loses one or more electrons, it becomes an ion, and its spectrum changes. Neutral hydrogen has one electron and produces the familiar Balmer and Lyman series. Ionized hydrogen, which is just a proton, doesn't absorb light at all in the visible or near infrared because it has no electrons to excite. But heavier elements can lose multiple electrons, and each ionization state has a different spectrum. In hot environments like the atmospheres of massive stars or the gas surrounding black holes, elements can be stripped of many electrons, creating highly ionized species. Iron can lose over 20 electrons, becoming Fe1 or Fe2 in spectroscopic notation. These ions have spectral lines in the X-ray and ultraviolet parts of the spectrum. Some also have lines in the infrared, though they're usually faint. The team investigated whether the signal could come from highly ionized heavy elements. They modeled clouds of ionized carbon, nitrogen, oxygen, neon, magnesium, silicon, sulfur, and iron, checking whether any combination could produce the observed pattern. Once again, no match. The wavelengths and spacing of the lines didn't fit. And even if they did, there was a bigger problem. Creating such high ionization states requires intense radiation or extreme temperatures, which would make the source hot, not cold. Molecular spectroscopy was also considered. Molecules are more complex than atoms because they have additional energy levels from rotation and vibration. A diatomic molecule like carbon monoxide can spin around its center of mass and oscillate like a spring, and each of these motions has quantized energy levels. When molecules absorb or emit light, they can change their rotational and vibrational states, producing intricate patterns of closely spaced spectral lines called bands. In the cold clouds of interstellar space, molecules like H2, Colorado, H2O, NH3, and more complex organics produce absorption and emission features in the infrared. The James Webb Space Telescope was specifically designed to detect these molecules, particularly in the atmospheres of exoplanets where they might indicate habitability or even life. The spectroscopists on the team compiled every known molecular spectrum and compared them to the signal. Nothing fit. They even considered exotic molecules that have been detected in space but are rare on Earth. Carbon chains like HC3N, ring molecules like CC3H2, and even more complex polycyclic aromatic hydrocarbons, or PAHs. These molecules can produce complex spectra, but again, the observed pattern didn't match. It wasn't close enough to be explained by a combination of known molecules with some redshift or temperature effect. One particularly creative idea was that the signal might involve molecules in unusual quantum states. In very cold environments, molecules can exist in highly excited rotational or vibrational states if they've been pumped by specific wavelengths of radiation. Masers and lasers, which are microwave and optical versions of this phenomenon, occur naturally in space when molecules are stimulated by starlight or collisions. Perhaps the signal came from molecules in some metastable state, trapped in high energy levels and producing unusual spectral features as they relaxed. This was an intriguing idea, but modeling it required assumptions about the molecular species, the pumping mechanism, and the density and temperature of the gas. No combination of parameters produced a spectrum matching the observations. And it still didn't explain the fundamental mystery. What molecules were involved? If they were known molecules in strange states, the spectrum should still resemble the known molecular fingerprints, just distorted. But the observed lines had no resemblance to anything in the databases. As the chemical mystery deepened, some scientists began to whisper about a possibility that most were reluctant to say aloud. What if the spectral lines weren't natural at all? What if they represented something intentionally created, a pattern embedded in the signal to convey information? In SETI research, scientists have long speculated about how an alien civilization might encode a message. One method is to use specific frequencies or wavelengths that stand out against the natural background. Another is to create patterns that couldn't occur by chance, like prime numbers or mathematical constants. The Webb signal had a pattern. The absorption lines were spaced at irregular intervals, not the regular spacing you'd expect from a single element or simple molecule. But they weren't random either. There seemed to be structure, clusters of lines separated by gaps, some lines stronger than others. A few researchers started analyzing the pattern mathematically, looking for sequences, ratios, or correlations that might indicate design rather than chemistry. The results were inconclusive, but they couldn't rule out the possibility that the signal was artificial. Early universe cosmology and timing issues. The signal's redshift placed it at a look-back time of 13.2 billion years, just 600 million years after the Big Bang. This is an era known as the Cosmic Dawn, when the first stars and galaxies began to form, and the universe transitioned from darkness to light. Webb was specifically designed to study this period because it represents a frontier we've never been able to observe in detail. But finding an anomalous signal from this epoch raised profound questions about what could exist so early in cosmic history. To understand why the timing was problematic, we need to review what we know about the early universe. The Big Bang occurred 13.8 billion years ago, marking the beginning of space, time, matter, and energy. In the first moments, the universe was unimaginably hot and dense, a plasma of quarks and gluons. As it expanded and cooled, quarks combined to form protons and neutrons. After about 3 minutes, protons and neutrons fused to create the first atomic nuclei, mostly hydrogen and helium with trace amounts of lithium. This process is called Big Bang nucleosynthesis. For the next 380,000 years, the universe remained a hot plasma, opaque to light because photons couldn't travel freely. Then came recombination, when electrons and nuclei combined to form neutral atoms. The universe became transparent, and the cosmic microwave background was released. After that, there was a period called the Dark Ages. The universe had cooled enough that atoms existed, but no stars had formed yet. It was filled with neutral hydrogen gas, dark and featureless. The Dark Ages lasted several 100 million years. During this time, tiny density fluctuations in the gas, seeded by quantum fluctuations in the very early universe, began to grow under gravity. Regions slightly denser than average attracted more matter, becoming denser still. Eventually, the gas collapsed into the first stars, probably massive and short-lived, shining with intense ultraviolet radiation. These first stars began to ionize the surrounding hydrogen, creating bubbles of ionized gas. As more stars formed and more bubbles grew, they merged, and eventually the entire universe was reionized. This period, called the Epoch of Reionization, spanned from about 200 million to 1 billion years after the Big Bang. By the time the universe was 1 billion years old, galaxies were common. Supermassive black holes had formed in their centers, and the large-scale structure we see today was beginning to take shape. The signal Webb detected came from 600 million years after the Big Bang, right in the middle of the Epoch of Reionization. At this time, the universe was young but not empty. The first galaxies had formed, and the first generation of stars had lived and died, seeding the cosmos with heavier elements. But the universe was still very different from today. Galaxies were smaller, more irregular, and actively forming stars at high rates. The intergalactic medium was a mix of neutral and ionized hydrogen, and the chemical composition was dominated by hydrogen and helium, with only trace amounts of heavier elements. Given these conditions, what could produce the signal Webb observed? If it was a natural object, it had to form within 600 million years. That's not much time on cosmic scales. Stars can form in a few million years. Galaxies take tens to hundreds of millions of years to assemble. Supermassive black holes grow over hundreds of millions to billions of years. Unless they form through some exotic process we don't understand. But the signal didn't resemble any of these objects. If it was a galaxy, even a very unusual one, it should show signs of stars. Hot, massive stars emit ultraviolet light, which would be redshifted into the optical and near-infrared by the time it reaches us. We should see spectral features from hydrogen, helium, and perhaps a few heavier elements. We should detect thermal emission from dust heated by starlight. The signal showed none of this. It was cold, chemically bizarre, and lacked any of the typical signatures of a young galaxy. Could it be a supermassive black hole? These objects are known to exist in the early universe. Webb and other telescopes have detected quasars, extremely luminous objects powered by black holes accreting matter at redshifts greater than 6, corresponding to times less than 1 billion years after the Big Bang. The existence of billion solar mass black holes so early is itself a puzzle, because growing from stellar mass seeds to such enormous sizes in such a short time is difficult, but at least we know they exist. However, the signal didn't resemble a quasar either. Quasars are among the brightest objects in the universe, powered by matter falling into black holes at tremendous rates. They emit across the entire electromagnetic spectrum, from radio waves to gamma rays, with peak emission in the ultraviolet and X-ray. They have characteristic spectra with broad emission lines from fast-moving gas and a bright continuum from the hot accretion disk. The Webb signal had none of these features. It was dim, cold, and showed only absorption lines, not emission. Perhaps it was a remnant from some process in the very early universe, something that formed before stars and galaxies. In the first moments after the Big Bang, the universe was filled with exotic particles and fields that no longer exist today. As the universe expanded and cooled, most of these particles decayed or annihilated, but perhaps some small fraction survived, clustering together to form structures we've never observed. This was pure speculation, but it was one of the few ideas that could account for the signal's age. The problem was that we have strong constraints on what happened in the early universe. Observations of the cosmic microwave background tell us about the density, temperature, and composition of the universe when it was 380,000 years old. Measurements of light element abundances tell us about conditions when the universe was 3 minutes old. Theories of inflation make predictions about even earlier times. None of these observations or theories predict the existence of cold, chemically unusual structures at redshift 8. Some cosmologists proposed that the signal could be related to dark matter. Dark matter makes up about 85% of the matter in the universe, but we don't know what it's made of. It doesn't emit, absorb, or scatter light in any way we've detected, which is why it's called dark. But it does have gravity, and it played a crucial role in forming the first structures. Dark matter clumped together first, creating gravitational wells into which normal matter fell, eventually forming stars and galaxies. What if dark matter wasn't entirely dark? Some theories propose that dark matter particles can decay or annihilate, producing photons or other particles. If this happened in the early universe, it might create signals that don't fit our expectations. Perhaps the Webb signal came from a region where dark matter was concentrated and undergoing some process that made it partially visible. This was an exciting idea, but it had problems. Dark matter interactions are incredibly weak, and even if they produced photons, the signal should be diffuse and faint, spread across large regions of sky, not concentrated in a single point like the Webb observation. Another possibility involved primordial black holes, hypothetical black holes that formed in the first fraction of a second after the Big Bang from density fluctuations in the primordial plasma. Unlike black holes from stellar collapse, primordial black holes could have any mass, from microscopic to thousands of solar masses. If they existed, they could have influenced structure formation in the early universe, seeding the formation of the first stars and galaxies. Some researchers have even suggested that primordial black holes could account for some or all of dark matter. If a primordial black hole was present in the region Webb observed, could it produce the signal? Black holes themselves don't emit light except through Hawking radiation, which is far too weak to detect for any black hole larger than microscopic. But black holes can accrete matter, and the infalling matter emits radiation as it heats up. If a primordial black hole was pulling in gas from the early universe, it might create an accretion disk with unusual properties. But again, this should produce a hot, bright signal with broad emission lines, not the cold absorption spectrum Webb detected. The timing issue also raised questions about cosmic evolution. The universe at redshift 8 was fundamentally different from today. The density of matter was higher, the temperature was higher, and the chemical composition was simpler. These conditions affect what kinds of objects can form and how they behave. In the modern universe, we see a rich diversity of structures: spiral galaxies, elliptical galaxies, star clusters, nebulae, planets, asteroids. But at redshift 8, this diversity hadn't yet developed. The first galaxies were small, irregular, and actively star-forming. The first black holes were growing. The first heavy elements were being synthesized in supernovae. Given these constraints, the signal seemed out of place. It was like finding a modern smartphone in an archaeological dig from ancient Egypt. The technology didn't match the era. If the signal was natural, it required conditions or processes that shouldn't exist at that time. If it was artificial, it implied a level of advancement that seems impossible for a civilization only 600 million years old when measured in cosmic time. This led some researchers to question whether the redshift measurement was correct. Redshift is determined by identifying spectral lines and comparing their observed wavelengths to their known rest frame wavelengths. The fractional shift gives you the redshift, and from that, you can calculate the distance and look-back time using models of cosmic expansion. But the Webb signal had unidentified spectral lines. If we didn't know what elements or molecules produced them, we couldn't determine their rest frame wavelengths, and we couldn't calculate a reliable redshift. Perhaps the source was much closer, and the apparent redshift was an illusion caused by some other effect. Gravitational redshift, for instance, can shift light to longer wavelengths if it escapes from a strong gravitational field. If the source was near a massive object, its light would be gravitationally redshifted, making it appear more distant than it really is. But this would require an extremely strong gravitational field, something like a neutron star or black hole, and there was no evidence of such an object in the vicinity. Another possibility was that the signal wasn't redshifted at all, but the spectral lines were intrinsically at those wavelengths. Perhaps the source emitted light in the mid-infrared for reasons having nothing to do with distance or cosmic expansion. If so, it could be much closer, possibly even within our galaxy or a nearby galaxy. But this raised new questions. What natural process produces absorption lines at random infrared wavelengths? And why had no other telescope ever detected this object? The timing issues remained unresolved. Whether the signal came from the early universe or from somewhere closer, its properties defied explanation. It was too cold, too chemically strange, and too unlike anything we expected. And the more researchers tried to fit it into our understanding of cosmic evolution, the more it resisted. Gravitational lensing and alternative explanations. When conventional explanations fail, astronomers often turn to gravitational lensing, one of the most powerful and counterintuitive predictions of general relativity. Massive objects warp space-time around them, bending the paths of light rays that pass nearby. This can magnify distant objects, distort their shapes, and even create multiple images. Could lensing explain the signal Webb detected? Gravitational lensing occurs when a massive object, like a galaxy or cluster, lies between us and a more distant source. The gravity of the foreground object acts like a lens, focusing light from the background source. If the alignment is perfect, the background source can appear as a complete ring, called an Einstein ring. More often, the alignment is imperfect, and the lensing creates distorted arcs or multiple images. Lensing is incredibly useful in astronomy. It allows us to see objects that would otherwise be too faint to detect. It also provides information about the mass distribution of the lensing object, including dark matter that can't be seen directly. Some of the most distant galaxies ever observed were only detectable because a foreground cluster magnified their light by factors of 10 or more. The team investigated whether the Webb signal could be a lensed background object. They searched for foreground structures that could act as lenses, galaxies, clusters, or even massive dark matter halos. Surveys of the region revealed a few galaxies at lower redshifts, but none were massive enough or positioned correctly to produce significant lensing. Moreover, lensing magnifies the brightness and can distort the shape, but it doesn't change the spectrum. A lensed object should still have the same spectral features as the unlensed version, just brighter. The mysterious absorption lines would still need an explanation. There's a special case called microlensing, where a smaller mass, like a star or even a planet, passes in front of a background source and briefly magnifies it. Microlensing events are transient, lasting days to months, depending on the masses and alignment. If the Webb signal was caused by microlensing, it should vary over time as the alignment changes. The team checked observations from different epochs, but the signal appeared steady, not varying. This ruled out microlensing. Another lensing-related idea involved something called time delay. When a background source is lensed, light takes different paths to reach us depending on which image we're observing. Because the paths have different lengths and pass through different gravitational potentials, the light arrives at different times. If the background source varies, we see the same variation in each image, but offset in time. This effect has been used to measure the expansion rate of the universe by monitoring lensed quasars. Could the Webb signal be one image of a multiply-lensed source, with the other images too faint to detect or located outside the field of view? This seemed unlikely. Multiple images from strong lensing usually have comparable brightness, and they're located symmetrically around the lens. If one image was bright enough for Webb to detect, the others should be visible too. Weak lensing, which produces smaller distortions, doesn't create multiple distinct images. Researchers also considered exotic lensing scenarios. For example, if a primordial black hole passed between us and the source, it could briefly magnify the light, but this would be a transient event, and as noted, the signal appeared constant. Another idea was that a cosmic string, a hypothetical one-dimensional defect in spacetime, predicted by some models of the early universe, could act as a lens. Cosmic strings have never been detected, and their existence remains speculative, but if they were real, they could create unusual lensing patterns. Still, this didn't explain the signal's strange spectrum. Beyond lensing, astronomers explored whether the signal could be an instrumental artifact, some quirk of Webb's detectors, or data processing pipeline. Space telescopes are incredibly complex machines, and despite extensive testing, unexpected issues can arise. The Hubble Space Telescope, for instance, had a flawed mirror that wasn't discovered until after launch, requiring a servicing mission to correct. Webb itself experienced a micrometeorite impact shortly after deployment, damaging one of its mirror segments, though not enough to significantly affect performance. The team reviewed every stage of the observation and data reduction. They checked for cosmic ray hits, which can create spurious signals on detectors. They looked for scattered light from bright sources outside the field of view. They examined the calibration files to ensure the instrument response was properly characterized. They reprocessed the data using different algorithms and compared results. Everything checked out. The signal was real, not a glitch. Could it be contamination from a foreground object, something much closer than the signal appeared to be? Asteroids, comets, and dust clouds in our solar system can sometimes photobomb observations, creating infrared signals. But these objects move, and their positions change over hours or days. Webb's observations were taken over multiple days, and the signal remained in the same location on the sky, ruling out solar system contaminants. Interstellar clouds within our galaxy were another possibility. The Milky Way is filled with gas and dust, and some of these clouds are very cold, emitting in the far infrared. But interstellar clouds have well-known spectra, dominated by molecules like CO, H2O, and various carbon compounds. They don't produce the unidentified absorption lines seen in the Webb data. And if the source was in our galaxy, it should show parallax, a change in position relative to background stars as Earth orbits the Sun. No parallax was detected, suggesting the source was extragalactic. Some scientists proposed that the signal could be a new type of astrophysical object, something that exists but hasn't been recognized or categorized yet. Astronomy has a history of discovering unexpected phenomena. Pulsars, rapidly rotating neutron stars that emit beams of radiation, were discovered in 1967 and initially called LGM-1 for little green men because their precise periodic signals seemed artificial. Quasars were first identified in the 1950s as radio sources, but their nature wasn't understood until the 1960s, when they were recognized as the bright cores of distant galaxies powered by supermassive black holes. Fast radio bursts, brief flashes of radio emission from unknown sources, were discovered in 2007 and remain partially mysterious. Perhaps the Webb signal was a similar discovery, an object or phenomenon we've never seen before. But identifying a new class of object requires understanding what sets it apart and what physical processes produce its properties. In the case of pulsars, once we understood they were rotating neutron stars, we could predict their behavior and search for more. With quasars, realizing they were powered by black holes allowed us to study their physics and evolution. For the Webb signal, there was no such framework. The properties didn't fit any plausible astrophysical model. One particularly speculative idea involved wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe or even different universes. Wormholes are solutions to Einstein's equations, but they require exotic matter with negative energy density to remain stable. And there's no evidence such matter exists. If a wormhole existed and was somehow radiating or reflecting light, it might produce unusual signals. But this was science fiction territory, far beyond anything supported by observation or theory. As alternative explanations were proposed and rejected, the astronomical community found itself in an uncomfortable position. The signal was real, verified by multiple independent checks. It didn't fit any known class of object. It violated expectations about temperature, chemistry, and cosmic evolution, and every attempt to explain it away as lensing, artifacts, or foreground contamination had failed. The data was forcing scientists to confront the possibility that they were seeing something genuinely new, something that challenged the foundations of their understanding. The search for technological signatures. The idea that the Webb signal might be artificial was not taken lightly. Astronomers are trained to seek natural explanations first, and to be extraordinarily skeptical of claims about extraterrestrial intelligence. The history of false alarms is long. Every unexplained signal, from pulsars to fast radio bursts, has eventually been traced to natural astrophysical processes. But the Webb signal was different in important ways, and some researchers began to seriously consider the possibility that it was a technosignature, evidence of technology created by an intelligent civilization. The search for extraterrestrial intelligence, or SETI, has been ongoing since the 1960s. Most efforts focus on radio wavelengths, searching for narrow-band signals or patterns that wouldn't occur naturally. Radio waves travel well through interstellar space and require relatively little energy to generate, making them a logical choice for communication. But SETI also considers other wavelengths, including optical and infrared, and other types of signatures beyond deliberate transmissions. Technosignatures are any observable features that indicate the presence of technology. These could include radio or laser signals, atmospheric pollution from industrial activity, waste heat from energy use, or megastructures like Dyson spheres that capture a star's energy. The key is that technosignatures should be distinguishable from natural phenomena. They should show patterns, efficiencies, or characteristics that can only be produced by intelligent design. The Webb signal had features that caught the attention of SETI researchers. First, the absorption lines didn't match any known chemistry, which could suggest they were artificially created rather than produced by natural atomic or molecular transitions. Second, the combination of cold temperature and significant brightness was physically puzzling, possibly indicating active energy management or technology. Third, the signal came from a single point source rather than being diffuse, suggesting a concentrated origin. But these features alone weren't enough to claim a technosignature. Astronomers needed to apply rigorous criteria to distinguish between natural and artificial. One approach is to look for modulation or patterns in the signal. Natural sources like stars and galaxies emit relatively steady light, or they vary in predictable ways based on physical processes like rotation or pulsation. An artificial signal might be modulated to carry information, with changes in brightness, frequency, or polarization encoding a message. The team analyzed the Webb data for temporal variations, checking whether the signal changed over the observation period. The data showed no obvious variations, but the observation time was limited. Webb had only stared at this region for a few days. If the signal was modulated on longer timescales, weeks or months, they would need extended monitoring to detect it. Follow-up observations were planned to search for variability. Another test involved looking for narrow-band emission. Natural processes tend to produce broad spectral features because they involve many atoms or molecules with a range of velocities and energies. A laser, by contrast, emits at a very specific wavelength, creating a narrow line in the spectrum. Some SETI searches look for optical or infrared lasers that might be used for communication or energy beaming. The Webb signal showed absorption lines rather than emission, and while they were narrow, they weren't as narrow as laser lines. This didn't rule out technology, but it didn't strongly support it either. Polarization was another potential clue. Light can be polarized, meaning its electric field oscillates in a particular direction. Natural sources like stars and thermal emission are usually unpolarized or weakly polarized. But some technologies like lasers or radio transmitters produce highly polarized light. Webb's instruments don't measure polarization directly, but other telescopes could be used to check this. If the signal showed unusual polarization, it might indicate an artificial origin. The location of the signal also mattered. If it came from a star system, that would be more interesting than if it came from empty intergalactic space. SETI searches typically target stars, especially those similar to the Sun, because we expect life to develop on planets, and planets orbit stars. The region where Webb detected the signal didn't contain any obvious bright stars or galaxies, but at the distances involved, even a Sun-like star would be too faint to see individually. Higher resolution observations might reveal a host star or galaxy. Researchers also considered the energy required to produce the signal. Even at its faint level, the signal had traveled 13.2 billion light-years to reach us, if the redshift distance was correct. At such a distance, even a modest flux requires enormous luminosity at the source. Calculating the energy involved, assuming the signal was emitted isotropically in all directions, the total power output would be comparable to the luminosity of entire galaxies. This seemed impossibly high for a technological source. However, if the signal was beamed rather than broadcast in all directions, the required energy would be much lower. A civilization using a powerful laser or directed radio transmission could concentrate energy in a narrow cone, reaching tremendous distances without needing galaxy-scale power. This is the principle behind proposals for interstellar communication, using focused beams to maximize range while minimizing energy costs. If the Webb signal was a directed beam and we happen to lie in its path, the source might be using much more reasonable power levels. But this raised a new question. Why would a civilization at redshift 8 be beaming a signal in our direction? At the time that light was emitted, Earth didn't exist. The Sun hadn't formed. The Milky Way was still assembling. If the signal was directed at us, the civilization would have had to predict where we would be 13 billion years later. An impossibility. More likely, if the signal was a beam, it was aimed at something else, and we were simply in the way, intercepting it by chance. Some SETI researchers suggested the signal might not be a deliberate communication at all, but leakage from some other technology. Just as Earth's radio and television broadcasts leak into space, advertising our presence unintentionally, an advanced civilization might produce technosignatures as byproducts of their activities. Energy production, transportation, computation, whatever technologies they use, could emit radiation that escapes into space and becomes detectable across interstellar or even intergalactic distances. The problem with this interpretation was that our own leakage is decreasing over time. As we switch from broadcast television to cable and internet, from analog to digital, and from inefficient to efficient technologies, the amount of radiation we inadvertently send into space is dropping. A truly advanced civilization would likely have even less leakage, using closed systems and efficient energy management that minimize waste. Detecting their unintentional signals would be difficult unless we happened to observe during a brief window when they were technologically active, but not yet efficient. Another consideration was the Fermi paradox, the question of why we haven't detected any signs of extraterrestrial intelligence, despite the apparent high probability that they exist. The universe is vast and old, with billions of stars and potentially trillions of planets. If intelligent life is common, we should see evidence of it everywhere. The absence of such evidence has led to various explanations. Perhaps life is rare, perhaps intelligence is rare, perhaps civilizations destroy themselves before spreading, or perhaps they deliberately avoid contact. If the Webb signal was a technosignature, it would be the first confirmed detection of extraterrestrial intelligence, resolving the Fermi paradox in the most dramatic way possible. But it would also raise new questions. Why only one signal? Why from such an early epoch? And if civilizations existed that long ago, where are their descendants? A civilization 13 billion years old should have had time to spread across the galaxy or beyond, leaving traces that are more obvious than a single anomalous signal. For now, the technological interpretation remained speculative. The signal had unusual properties, but unusual doesn't automatically mean artificial. Extraordinary claims require extraordinary evidence, and the burden of proof was high. Astronomers needed more data, more observations, and more tests before they could even begin to seriously entertain the possibility that Webb had detected an alien transmission. Exotic physics and quantum phenomena. As natural astrophysical explanations continued to fail, some physicists began to wonder whether the signal might be evidence of exotic physics, phenomena that go beyond our current understanding of the Standard Model and general relativity. The universe is full of mysteries, dark matter, dark energy, the nature of quantum gravity, and it's possible that some of these mysteries could manifest in ways we haven't anticipated. One area of interest was vacuum decay. In quantum field theory, what we call empty space isn't truly empty. It's filled with quantum fields, and these fields have energy even in their ground state. This vacuum energy contributes to what we observe as dark energy, the mysterious force driving the accelerated expansion of the universe. But some theories suggest that our vacuum might not be in its true ground state. It could be in a metastable state, a false vacuum, that's stable for now but could decay to a lower energy state. If vacuum decay occurred, it would be catastrophic. A bubble of true vacuum would nucleate and expand at the speed of light, converting false vacuum to true vacuum and releasing enormous energy in the process. Inside the bubble, the laws of physics could be different, with altered constants and particle properties. Everything in the path of the expanding bubble would be destroyed and rebuilt according to new rules. The good news is that vacuum decay, if it's possible at all, is extraordinarily rare. The bad news is that we have no way to predict when or where it might happen. Could the Webb signal be related to vacuum decay? If a bubble had nucleated in the early universe and was expanding through space, the boundary between true and false vacuum might emit radiation as particles and fields adjusted to the new conditions. The spectrum could be unusual, reflecting physics in transition. The cold temperature might result from energy being consumed in the phase transition rather than radiated. This was a fascinating idea, but there were problems. Vacuum decay bubbles should expand at the speed of light, and if one had started 13 billion years ago, it would have engulfed us long ago. Unless the decay was incomplete or had stalled somehow, which seemed unlikely. Another exotic possibility involved cosmic strings, one-dimensional defects in space-time that could have formed during phase transitions in the very early universe. Cosmic strings are predicted by some models of particle physics, but have never been observed. If they exist, they would be incredibly dense, with masses comparable to mountain ranges, but concentrated in lines thinner than an atom. They would warp space-time around them, creating gravitational effects and potentially emitting radiation if they oscillated or interacted. Could a cosmic string produce the Webb signal? If a string was oscillating, it might radiate gravitational waves and possibly electromagnetic radiation. The spectrum could be unusual if the emission mechanism involved physics at energy scales far beyond what we can access in particle accelerators. But cosmic strings should produce bursts of energy rather than steady emission, and they should be associated with gravitational wave signatures that haven't been detected. Also, the signal's point-like appearance didn't match the expected geometry of a string, which should appear as a line across the sky. Quantum black holes were another speculative idea. In theories of quantum gravity, black holes might not be the purely classical objects described by general relativity. At the Planck scale, quantum effects become important, and the singularity at the black hole's center might be replaced by a quantum structure. Some models suggest that quantum black holes could emit radiation in unusual ways, not just through Hawking radiation, but through more exotic processes involving quantum entanglement or non-local effects. If a quantum black hole existed in the region Webb observed, it might produce a signal unlike anything from a classical black hole. The spectrum could reflect quantum transitions in the black hole's internal states. The cold temperature could result from the black hole being in a low energy state. But this required the existence of quantum gravity effects at macroscopic scales, something not predicted by any established theory. And it still didn't explain the specific pattern of absorption lines. Axions and other dark matter candidates were also considered. Axions are hypothetical particles proposed to solve certain problems in particle physics. They're extremely light and interact very weakly with normal matter, making them excellent dark matter candidates. If axions exist, they could clump together in dense clouds, and under certain conditions, they might convert to photons in the presence of magnetic fields through a process called the Primakov effect. This could create unusual electromagnetic signals. Could the Webb signal come from an axion cloud? If a large concentration of axions was converting to photons, it might emit at specific wavelengths determined by the axion mass and the local magnetic field strength. The signal could be cold if the axions themselves were in a low energy state, but calculating the expected signal from axion decay showed that it would be far too weak to detect at cosmological distances, and the spectrum wouldn't match the observed absorption lines. The idea was creative, but didn't fit the data. Some researchers explored whether the signal might be connected to the cosmological constant problem, one of the biggest unsolved questions in physics. The cosmological constant represents the energy density of empty space, and quantum field theory predicts it should be enormous, about 120 orders of magnitude larger than what we observe. This discrepancy is so vast that it's called the worst prediction in the history of physics. Various solutions have been proposed, from fine-tuning to anthropic arguments, but none are fully satisfactory. What if the Webb signal was a clue to solving this problem? Perhaps it came from a region where the vacuum energy was different, creating observable effects in the radiation or matter there. If the cosmological constant varied across space or time, it could affect how structures form and how light propagates. This might explain why the signal's properties seemed inconsistent with our models, because our models assume a constant vacuum energy. But proposing a varying cosmological constant required new physics, and there was no independent evidence for such variation. Quantum entanglement and non-locality were also invoked in some of the more speculative discussions. Entanglement is a quantum mechanical phenomenon where two particles become correlated in such a way that measuring one instantly affects the other, regardless of the distance between them. This has been verified in laboratories and is the basis for emerging technologies like quantum computing and quantum cryptography. But it's a subtle effect, typically observed in carefully controlled systems, not in astrophysical contexts. Could entanglement play a role in the Webb signal? Some theoretical physicists have proposed that quantum entanglement might be more fundamental than we realize, potentially connected to the structure of space-time itself. If entangled particles or fields were involved in the emission or absorption process, they might create correlations in the spectrum that appear unusual or non-random. This could explain the patterned nature of the absorption lines, but this was highly speculative, far beyond anything testable with current technology. Holography was another exotic concept that came up. The holographic principle, motivated by black hole thermodynamics and string theory, suggests that all the information in a volume of space can be encoded on its boundary surface. In this view, our three-dimensional universe might be a holographic projection of information stored in a lower dimensional space. If this is true, it could have observable consequences, though what those would be is unclear. Could the Webb signal be a holographic artifact, information leaking from the boundary into the bulk in an unusual way? This idea was so far removed from testable physics that most researchers dismissed it out of hand. But in the absence of conventional explanations, even wild ideas got a hearing. The holographic principle might one day lead to predictions about observable phenomena, but for now, it was a mathematical framework, not a practical tool for explaining anomalous astronomical signals. The discussions of exotic physics reflected both the frustration and the excitement of the situation. Frustration because every standard approach had failed to explain the signal. Excitement because the failure of standard approaches might mean they were on the verge of discovering something truly new. Throughout the history of science, unexplained observations have sometimes led to revolutionary discoveries. The orbit of Mercury didn't fit Newtonian gravity, leading Einstein to develop general relativity. The rotation curves of galaxies didn't fit visible matter, leading to the discovery of dark matter. Perhaps the Webb signal would be the next such breakthrough. But extraordinary claims require extraordinary evidence. Proposing new physics based on a single observation is premature. Researchers needed more data, independent confirmation, and alternative tests. They needed to rule out every possible conventional explanation before invoking exotic phenomena. And they needed to develop predictions that could be tested, ways to distinguish between competing ideas and eliminate the ones that don't work. Probing the Webb signal across the spectrum. Once the initial shock of the discovery wore off, the astronomical community mobilized to gather more data. If the signal was real and significant, it needed to be studied from every possible angle. Webb alone couldn't answer all the questions. Other telescopes, operating at different wavelengths and with different capabilities, were brought to bear on the mystery. The first priority was confirmation. Science operates on the principle of reproducibility. A result isn't truly trusted until it's been independently verified by others using different instruments or methods. Several teams requested time on other infrared telescopes to observe the same region of sky. The Spitzer Space Telescope had been retired, but ground-based observatories like the Keck telescopes in Hawaii and the Very Large Telescope in Chile had infrared capabilities. These facilities pointed their instruments at the coordinates and began collecting data. The ground-based observations faced challenges that Webb didn't. Earth's atmosphere absorbs much of the infrared spectrum, particularly at the wavelengths where the signal was strongest. Even at high-altitude sites with dry, stable air, atmospheric water vapor creates interference. Adaptive optic systems can correct for atmospheric distortion, but they can't eliminate absorption. Despite these limitations, the ground-based teams detected a faint source at the target location. It wasn't as clear as in Webb's data, but it was there, confirming that the signal was real and not an artifact of Webb's instruments. Next came multi-wavelength observations. The signal had been detected in the mid-infrared, but what about other parts of the spectrum? Radio telescopes like the Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile scanned the region at radio wavelengths. X-ray satellites, including XMM Newton and Chandra, pointed their detectors at the coordinates, searching for high-energy emission. Optical telescopes like Hubble and the ground-based Subaru telescope looked for any visible light. The results were puzzling. The radio observations detected nothing above the noise level. The X-ray satellites saw no signal. The optical telescopes found no bright sources, though there were a few faint galaxies in the field that could be unrelated foreground or background objects. It seemed the source was only emitting, or only detectable, in a narrow range of infrared wavelengths. This was unusual. Most astrophysical sources emit across a broad range of wavelengths, from radio to gamma rays, with the relative brightness in different bands, depending on the underlying physics. The fact that the signal was infrared only suggested it was either very cold, which matched the temperature estimates, or that something was selectively absorbing or scattering other wavelengths. If the source was embedded in a thick cloud of dust, the dust would absorb ultraviolet and optical light and re-radiate it in the infrared. But this should produce a characteristic spectrum dominated by thermal emission from warm dust, not the cold absorption line spectrum Webb observed. Time domain observations were also initiated. The initial Webb data was a snapshot, effectively a few days of observation. To check for variability, telescopes monitored the source over weeks and months. If the signal changed in brightness or spectrum, it could provide clues about the underlying process. Variable sources are common in astronomy: pulsars, variable stars, active galactic nuclei, and their variability patterns often reveal information about their structure and dynamics. After months of monitoring, the signal appeared constant. No periodic variations, no sudden flares or dips, just a steady, unchanging emission. This ruled out several classes of variable objects like pulsars or binary stars, but it didn't narrow down the possibilities significantly. Some objects, like distant galaxies or cold gas clouds, can remain constant over long timescales. The lack of variability was a clue, but not a definitive one. Polarization measurements were attempted using instruments on ground-based telescopes. Polarization can reveal information about magnetic fields, scattering processes, and the geometry of the emitting region. If the signal was highly polarized, it might suggest coherent emission like a laser or synchrotron radiation from relativistic particles in a magnetic field. If it was unpolarized, it likely came from thermal emission or random scattering. The polarization results were inconclusive. The signal was faint, and measuring polarization at infrared wavelengths from the ground is technically difficult. The data suggested weak polarization, consistent with thermal emission, but the uncertainties were large. Better polarization data would require space-based observations or specialized instruments that didn't yet exist. Spectroscopic follow-up was crucial. Webb's initial spectrum had limited resolution and wavelength coverage. Higher resolution spectra could reveal finer details, such as narrow subcomponents of the absorption lines or additional weak features. Telescopes with high-resolution spectrographs, including Keck and VLT, obtained deeper spectra of the source. The high-resolution data confirmed the presence of the mysterious absorption lines and revealed even more of them. Some lines were split into multiple components, suggesting complex structure or multiple velocity components in the absorbing material. But the patterns still didn't match any known element or molecule. Chemical databases were searched exhaustively. Researchers even considered combinations of multiple species, layered clouds with different compositions, or absorption from ionized metals in unusual states. Nothing worked. One interesting finding from the spectroscopy was that the line strengths varied slightly across the source. If the source had spatial structure, different parts might have different temperatures or compositions, leading to variations in the spectrum. But resolving the source spatially was difficult because it appeared so small on the sky. Webb's resolution was excellent, but even it couldn't clearly separate the source into distinct components. Interferometry, using multiple telescopes working together, might provide higher resolution, but no infrared interferometers were currently capable of observing at the required sensitivity and wavelength. Gravitational wave detectors were also informed about the discovery. If the signal was related to some exotic compact object or violent event, it might produce gravitational waves. LIGO and Virgo, designed to detect ripples in spacetime from merging black holes and neutron stars, had never seen anything like this before, but they agreed to analyze their data streams for any coincident signals. None were found, but the gravitational wave observatories operate at high frequencies, sensitive to stellar mass compact objects. A supermassive black hole or cosmological source would produce low-frequency gravitational waves that required space-based detectors like LISA, which wouldn't launch for another decade. Neutrino observatories like IceCube in Antarctica and Super Kamiokande in Japan also joined the effort. Neutrinos are nearly massless particles that interact very weakly with matter, allowing them to escape from dense environments where photons would be trapped. If the source involved high-energy processes like particle acceleration or nuclear reactions, it might emit neutrinos. But detecting neutrinos from a specific direction is challenging because they're so rare, and the detectors are optimized for high-energy events like supernovae or active galactic nuclei. No neutrinos were detected from the direction of the signal, which wasn't surprising given its faintness and the low probability of neutrino interactions. The coordinated observations created an unprecedented dataset. The source had been examined across the electromagnetic spectrum, from radio to gamma rays, and in multiple other channels like gravitational waves and neutrinos. Yet the picture remained incomplete. The source emitted only in a narrow infrared band, showed no variability, had weak or absent polarization, and had a spectrum that defied identification. It was as if the universe was deliberately hiding the nature of this object, revealing just enough to tantalize, but not enough to explain. When scientists went to war over the data. As data accumulated, the scientific community began to fracture into camps, each advocating for different interpretations of the signal. Conferences and workshops were organized to bring researchers together, share data, and debate the possibilities. The atmosphere was electric, a mix of excitement, skepticism, and frustration. Everyone agreed the signal was real and anomalous. What they couldn't agree on was what it meant. One camp argued for a conservative interpretation. These researchers believed the signal must have a natural astrophysical explanation, even if we hadn't figured it out yet. History showed that unusual observations almost always turned out to be natural phenomena once better data or better models became available. The signal's properties were strange, yes, but not impossible. Perhaps it was a new type of galaxy with unusual chemistry. Perhaps it was a cold molecular cloud illuminated by background radiation in an unexpected way. Perhaps it involved processes we understood individually, but had never seen combined in this particular configuration. This conservative camp pointed to examples from the past where anomalous observations were eventually explained. The canals on Mars, seen by astronomers in the late 19th and early 20th centuries, turned out to be optical illusions. The planet Vulcan, proposed to explain irregularities in Mercury's orbit, didn't exist. The irregularities were explained by general relativity. The WOW signal from 1977, a strong radio signal detected by SETI that lasted 72 seconds, remains unexplained but is widely believed to be either a natural phenomenon or terrestrial interference, not aliens. The conservative researchers argued for patience. More observations, better instruments, and refined models would eventually crack the mystery. Jumping to exotic explanations, especially involving new physics or extraterrestrial intelligence, was premature and potentially embarrassing. Science had a responsibility to be cautious, to exhaust conventional explanations before considering unconventional ones. A second camp took a more radical view. These scientists argued that the signal's properties were so unusual that invoking new physics was not just warranted but necessary. The temperature anomaly, the unidentified spectral lines, the timing in cosmic history, these weren't minor puzzles, but fundamental contradictions. Conventional astrophysics couldn't explain them, which meant either our understanding was incomplete or our observations were revealing something genuinely new. This radical camp proposed various exotic scenarios. Some favored dark matter interactions, suggesting that the signal came from a region where dark matter was concentrated and interacting with normal matter in ways not predicted by current models. Others preferred primordial black holes or cosmic strings, relics from the early universe that had never been directly observed but were allowed by physics. A few even suggested that the signal might be evidence of physics beyond the standard model, involving particles or forces we haven't discovered yet. The debates between these camps grew heated. At conferences, presentations were met with sharp questions and skeptical comments. Papers submitted to journals faced intense peer review, with referees demanding more evidence, better controls, and stronger arguments. Online forums and social media saw astronomers and physicists arguing about data quality, statistical significance, and theoretical plausibility. The controversy spilled into the popular press, with headlines alternating between new cosmic mystery and scientists clash over space signal. A third, smaller camp occupied a middle ground. These researchers acknowledged that the signal was unusual, but argued that the available data was still insufficient to draw strong conclusions. They called for more observations, particularly higher resolution spectroscopy, spatial imaging, and long-term monitoring. They emphasized the need for systematic studies to rule out instrumental artifacts, foreground contamination, and selection effects. Only with better data could the community decide between competing explanations. This middle camp also warned against confirmation bias, the tendency to interpret ambiguous data in ways that support one's preferred hypothesis. If you believed the signal was a new type of galaxy, you might focus on features consistent with that idea and downplay inconsistencies. If you believed it was extraterrestrial, you might see patterns and structures that were actually noise. Good science required considering all possibilities objectively and letting the data decide. The SETI community was divided as well. Some SETI researchers were excited by the possibility that the signal might be a technosignature, the first confirmed detection of extraterrestrial intelligence. They pointed to the signal's unusual properties as exactly the kind of thing SETI should be looking for, something that doesn't fit natural models and might indicate technology. They proposed follow-up searches for additional signals, modulation patterns, or associated phenomena that could strengthen the case for artificiality. Other SETI researchers were more cautious. They noted that the field had a long history of false alarms, signals that seemed artificial at first but turned out to be natural or man-made. Pulsars, as mentioned, were initially called LGM-1 for little green men, because their precise periodicity seemed too perfect to be natural. Fast radio bursts caused excitement when first discovered, with some speculating they might be alien transmissions, but they're now understood as natural astrophysical events, probably from magnetars. The lesson was clear. Extraordinary claims about extraterrestrial intelligence required overwhelming evidence, not just an unexplained observation. The debate over statistical significance was particularly contentious. In science, observations are considered significant if they're unlikely to occur by chance. The standard threshold is a p-value of 0.05 or better, meaning there's less than a 5% probability that the result is a statistical fluke. For extraordinary claims, higher standards are applied, often requiring p-values of 0.001 or even lower, corresponding to 5 sigma significance in particle physics. How significant was the Webb signal? It had been detected by multiple independent observations, confirmed by ground-based telescopes, and analyzed by different teams using different methods. The probability that it was a random fluctuation or instrumental artifact was extremely low, probably less than 1 in a million. In that sense, it was highly significant, but statistical significance doesn't equal importance or novelty. A highly significant detection of something boring is still boring. The question was whether the signal represented something new and important, not just whether it was real. Critics of the more exotic interpretations argued that the data, while unusual, didn't meet the burden of proof for claims about new physics or extraterrestrial intelligence. They pointed out that the spectral lines, while unidentified, might simply be from known species in unusual conditions that hadn't been properly modeled yet. The cold temperature might result from some subtle radiative transfer effect that hadn't been considered. The source's location at high redshift might be a misinterpretation of the data. Without definitive proof, the simplest explanation remained that this was a natural object we didn't fully understand yet. Proponents of exotic explanations countered that the conservative approach was too rigid. Science progressed by considering new ideas, not by clinging to old frameworks. If every anomaly was dismissed as probably something we'll figure out later, genuine discoveries would be overlooked. The Webb signal deserved serious consideration of all possibilities, including the unconventional ones, because ruling them out was just as important as confirming them. Only by testing radical ideas could science advance. The debate also touched on philosophical questions about the nature of evidence and the standards for accepting new phenomena. How much evidence is enough? How unusual does an observation have to be before we invoke new physics? How do we balance skepticism and open-mindedness? These aren't easy questions, and different scientists have different thresholds based on their training, experience, and personal philosophy. Some researchers invoked Bayesian reasoning, a statistical framework that updates beliefs based on new evidence. In Bayesian terms, the probability of a hypothesis depends not just on how well it fits the data, but also on its prior probability, how likely it seemed before the data was collected. Exotic hypotheses like new physics or aliens have very low prior probabilities because they require overturning well-established science or assuming something we've never observed. Even if they fit the data well, their low priors mean the posterior probability, the updated belief after seeing the data, remains low unless the data is overwhelmingly compelling. Others argued that Bayesian priors were subjective and could lead to conservatism that stifled innovation. If you assigned extremely low prior probability to new phenomena, no amount of evidence would convince you they existed. This was the mindset that delayed acceptance of continental drift, despite clear geological evidence, because the idea seemed implausible to many scientists. A better approach, they argued, was to focus on the likelihood, how well different hypotheses explain the data, and let that guide decisions. As the debates raged, a few voices called for unity. The astronomical community, they argued, should work together rather than fracture into camps. The signal was an opportunity, a chance to push the boundaries of knowledge, but only if researchers collaborated, shared data openly, and tested ideas rigorously. Infighting and tribalism would only slow progress and damage the credibility of the field. These calls for unity had mixed success. Some collaborations formed, bringing together observers, theorists, and experts in instrumentation to tackle specific questions. Joint papers were published, analyzing the data from multiple perspectives and exploring different interpretations. But the fundamental disagreements remained. Until new data or new insights broke the deadlock, the community would remain divided, each camp convinced they were right and the others were missing the point. Machine learning tackles an infrared anomaly. As traditional methods struggled to make sense of the Webb signal, researchers turned to a new set of tools: machine learning and artificial intelligence. Over the past decade, AI has revolutionized many fields, from image recognition to language translation to drug discovery. Astronomy, with its vast datasets and complex patterns, has been a natural application area. Could AI succeed where human intuition and conventional analysis had failed? Machine learning works by training algorithms on large datasets, teaching them to recognize patterns and make predictions. In astronomy, ML has been used to classify galaxies, identify exoplanet transits, detect gravitational wave signals, and discover new pulsars. The advantage of ML is that it can find patterns that humans might miss, especially in high-dimensional data where visualizing all the variables at once is impossible. The disadvantage is that ML can also find spurious patterns. artifacts of the training process rather than real features of the data. Several teams applied ML techniques to the Webb signal. One approach was to use supervised learning, where the algorithm is trained on known examples and then tested on new data. Researchers compiled a database of spectra from every type of astronomical object: stars, galaxies, quasars, nebulae, supernovae, and more. They trained a neural network to classify spectra based on their features, learning to distinguish between different object types. Then they fed in the Webb signal and asked the network to classify it. The results were inconclusive. The neural network gave low confidence scores for all categories, indicating that the signal didn't resemble any of the training examples closely. The closest matches were to cold molecular clouds and distant galaxies, but even those had confidence levels below 50%. The algorithm essentially said, "I don't know what this is. It doesn't look like anything I've seen before." This was consistent with the human analysis, but didn't provide new insights. Another team tried unsupervised learning, where the algorithm looks for patterns without being told what to look for. They used a technique called clustering, which groups similar objects together based on their properties. The idea was to see if the Webb signal clustered with any known class of objects, or if it formed its own unique cluster. The algorithm processed thousands of spectra, including the Webb signal, and organized them into groups. The Webb signal ended up in a cluster of its own, isolated from everything else. A few other unusual spectra, mostly from poorly understood objects or noisy observations, were weakly associated with it, but nothing formed a clear category. This reinforced the idea that the signal was truly anomalous, not just a variant of something known. But again, it didn't explain what the signal was, only that it was different. A more sophisticated approach involved generative models, algorithms that can create new data similar to the training set. Researchers trained a variational autoencoder on spectral data, teaching it to compress spectra into a lower dimensional representation and then reconstruct them. The idea was that if the model could reconstruct the Webb signal, it meant the signal's features were within the range of known astrophysics, even if the specific combination was unusual. If the reconstruction failed, it would suggest the signal contained features outside the model's understanding. The VAE struggled to reconstruct the Webb signal. It could approximate the overall shape of the spectrum, the cold blackbody continuum, but it couldn't reproduce the absorption lines accurately. The reconstructed spectrum had lines in roughly the right places, but the strengths and profiles were wrong. This suggested that the signal's spectral features were genuinely unusual, not easily explained by combinations of known physical processes. Some researchers used AI to search for patterns within the absorption lines themselves. They applied techniques from signal processing and information theory, looking for regularities, periodicities, or correlations that might indicate structure. If the lines were artificial, perhaps encoding information, there might be mathematical patterns that AI could detect. The analysis found some intriguing hints. The spacing between certain lines showed weak correlations, and the ratios of line strengths had non-random distributions. But whether these patterns were meaningful or just statistical noise was unclear. Human pattern recognition is notoriously fallible, seeing faces in clouds and signals in randomness. AI can be similarly misled, especially if the training data or the search algorithms introduce biases. To test the significance of the patterns, researchers generated synthetic spectra with random absorption lines and ran the same AI analysis. Some of the synthetic spectra showed similar correlations and patterns, suggesting that the features in the Webb signal might be artifacts of the analysis method rather than real structures. Others argued that the comparison wasn't fair because real astrophysical spectra aren't truly random. They have physical constraints that synthetic data might not capture. Natural language processing, a branch of AI used to analyze text, was also adapted for spectral analysis. Researchers treated spectral lines as words and spectra as sentences, applying algorithms designed to find meaning in language. The idea was to see if the signal's sentence had a structure or grammar that could be decoded. This was a long shot, but some SETI researchers had proposed similar approaches for analyzing potential alien messages. The NLP algorithms found that the Webb signal had low entropy, meaning it wasn't completely random, but they couldn't extract any coherent meaning. The patterns were too ambiguous, and without knowing the language or encoding scheme, decoding was impossible. This didn't rule out the possibility of an encoded message, but it didn't support it either. The low entropy could just as easily result from physical constraints on the emitting or absorbing material. AI was also used to optimize observing strategies. Given limited telescope time and many possible follow-up observations, which should be prioritized, researchers developed reinforcement learning algorithms that simulated different observing scenarios and learned to choose the ones most likely to yield useful information. The AI suggested focusing on high-resolution spectroscopy at specific wavelengths where the absorption lines were strongest, and on monitoring the source for variations at timescales that previous observations might have missed. These AI-guided observations were carried out, and they did provide some new data. The high-resolution spectra revealed additional weak lines and confirmed the complex structure of the stronger ones, but they didn't crack the mystery. The AI had optimized the observations efficiently, but it couldn't create information that wasn't there, if the source simply didn't vary, or if its spectrum was intrinsically ambiguous. No amount of clever observing would resolve it. One of the most ambitious AI projects involved simulating the early universe and searching for scenarios that could produce the signal. Researchers used supercomputers to run thousands of cosmological simulations, varying parameters like the dark matter density, the initial density fluctuations, the star formation efficiency, and the chemical enrichment history. Each simulation produced a population of galaxies and other structures at various redshifts. AI algorithms then generated synthetic spectra for these objects and compared them to the Webb signal. The goal was to find a simulation that produced a match, which would reveal the physical conditions needed to create the signal. Unfortunately, none of the simulations came close. Even when parameters were tuned to extreme values, pushing the boundaries of what current cosmology allows, the synthetic spectra didn't match. This suggested that either the signal required conditions outside the range of simulations, or it wasn't a product of standard cosmological processes at all. Despite the impressive computational power and sophisticated algorithms, AI didn't solve the mystery. It confirmed what human researchers already suspected. The signal was anomalous and didn't fit conventional models. But AI did contribute in meaningful ways. It ruled out many hypotheses efficiently, guided observing strategies, and provided quantitative measures of how unusual the signal was. Perhaps most importantly, it demonstrated that even our most advanced analytical tools couldn't explain this phenomenon, underscoring its profound strangeness. Implications for SETI and the search for life. The possibility, however remote, that the Webb signal might be a technosignature reignited debates about the search for extraterrestrial intelligence and what we should expect to find. SETI had been operating for over 6 decades, primarily listening for radio signals from nearby stars. The Webb signal, if artificial, was completely different, an infrared signal from the early universe, 13 billion years old and billions of light years away. If this was how alien civilizations made themselves known, SETI might have been looking in the wrong places all along. Traditional SETI focuses on electromagnetic transmissions, particularly in the radio spectrum. The reasoning is sound. Radio waves travel well through interstellar space. They're relatively easy to generate with technology, and certain frequencies, like the 21-centimeter line of neutral hydrogen, are universal constants that any technological civilization might recognize. By monitoring these frequencies, SETI hopes to detect deliberate transmissions from nearby stars, perhaps messages intended for civilizations like ours. But this approach makes assumptions. It assumes that alien civilizations want to communicate, that they use radio, and that they're transmitting at frequencies and times we happen to be listening. The Webb signal, if artificial, challenged all these assumptions. It wasn't radio, it was infrared. It wasn't from a nearby star, it was from the distant universe. And it wasn't obviously a message, it was an anomalous spectrum that we could barely detect. Some SETI researchers argued that this was exactly why we needed to broaden our search strategies. Looking only for radio signals from sun-like stars within a few hundred light-years was too narrow. Civilizations might use optical lasers, gravitational wave transmitters, neutrino beams, or methods we haven't imagined. They might be billions of years old and span entire galaxies, not confined to single star systems. They might leave artifacts or technosignatures that persist long after the civilization itself has gone extinct or moved on. This idea, often called cosmic archaeology, focuses on searching for remnants rather than active transmissions. An advanced civilization might build megastructures like Dyson spheres, which would absorb visible light from a star and re-emit it in the infrared, creating an unusual spectral signature. They might alter the atmospheres of planets, filling them with industrial pollutants or synthetic chemicals that wouldn't exist naturally. They might even leave beacons, automated devices designed to last millions or billions of years, broadcasting into space long after their creators were gone. The Webb signal, with its strange spectrum and ancient origin, fit this paradigm better than traditional SETI signals. If it was artificial, it likely wasn't a message directed at us. It might be a byproduct of some technology, a beacon, or a remnant of a long-dead civilization. The absorption lines might encode information, or they might simply be the spectral signature of exotic materials or processes used by the civilization. But why would a civilization so old and so distant leave a signal that we could detect? One possibility was that they were extraordinarily powerful, capable of engineering on galactic scales, producing effects visible across the universe. Another was that the signal was unintentional leakage, like our own radio and television broadcasts that leak into space. A third was that the signal was deliberate but not meant for us, aimed at some other target that we happened to intercept. The implications for the Drake equation were significant. The Drake equation estimates the number of communicative civilizations in our galaxy by multiplying factors like the star formation rate, the fraction of stars with planets, and the fraction of planets where intelligence evolves. Depending on the values chosen, the equation predicts anywhere from 0 to millions of civilizations. SETI's lack of detections had suggested the lower end of that range, but the Webb signal, if confirmed as artificial, would dramatically shift the probabilities. If civilizations existed 13 billion years ago, when the universe was less than 5% of its current age, then intelligence must be common. The timescales for evolution would be much shorter than we thought, or intelligent life emerged under conditions very different from Earth. This would boost several factors in the Drake equation, particularly the fraction of planets where life develops and the fraction where intelligence arises. Even if most civilizations were short-lived, the sheer number of opportunities would mean the galaxy should be teeming with intelligence, past or present. But this raised the Fermi paradox again, with renewed urgency. If advanced civilizations existed billions of years ago, where are they now? Where are their descendants, their artifacts, their impacts on the cosmos? A civilization with a 13 billion year head start should have colonized the galaxy, spread to neighboring galaxies, and left traces everywhere. Yet aside from one ambiguous signal, we see nothing. One explanation was the Great Filter, a hypothetical barrier in the development of life from simple replicators to galaxy-spanning civilizations. If the filter was behind us in the past, it meant that developing technological intelligence was incredibly rare, and we were lucky. If it was ahead of us, it meant that civilizations typically destroy themselves or face insurmountable challenges before becoming spacefaring. The Webb signal, coming from the early universe, suggested the filter might be ahead. Perhaps that civilization had risen, flourished briefly, and then vanished, leaving only this faint trace. Another explanation invoked the zoo hypothesis, the idea that advanced civilizations deliberately avoid contact with less developed ones, perhaps to allow natural development or as part of some ethical code. If such a policy existed, ancient civilizations might leave only subtle or ambiguous traces, enough to tantalize but not to reveal themselves fully. The Webb signal could be such a trace, a hint that we're not alone, but not a definitive proof. The simulation hypothesis was also discussed. Some philosophers and physicists have speculated that we might be living in a computer simulation created by an advanced civilization. If true, anomalies like the Webb signal could be deliberate insertions, Easter eggs planted by the simulators to provoke thought or test our reactions. This idea was far-fetched and unfalsifiable, but it gained attention in the context of unexplainable observations. For astrobiologists, the signal raised questions about the nature of life and intelligence. Life on Earth is carbon-based, relies on liquid water, and evolved over billions of years through natural selection. But is this the only way? Could life develop faster under different conditions? Could it be based on silicon, sulfur, or entirely different chemistry? Could intelligence emerge without biology, perhaps in the form of self-replicating machines or exotic energy patterns? The Webb signal's strange chemistry and cold temperature might hint at non-biological processes. If it was a technosignature, it might come from machines, not organisms. An ancient civilization could have transitioned from biological to synthetic life, creating autonomous systems that outlived their creators. These machines might operate at cold temperatures for efficiency, use materials and energy sources we don't recognize, and leave spectral signatures unlike anything biological. The search for biosignatures, chemical markers of life in the atmospheres of exoplanets, was also influenced by the discovery. If life could be so radically different from Earth's, then focusing only on oxygen, methane, and water might miss exotic forms of biology. The James Webb Space Telescope was designed to analyze exoplanet atmospheres, searching for gases that might indicate life. The signal reminded researchers to keep an open mind about what biosignatures might look like. Some scientists proposed new SETI strategies based on the Webb discovery. Instead of listening for radio signals from nearby stars, why not search for anomalous infrared emissions from distant galaxies? Instead of assuming aliens use technology similar to ours, why not look for anything unusual, anything that defies natural explanation? This approach, sometimes called weird object astronomy, would cast a wider net, searching for the unexpected rather than the predicted. The risk was false positives and wasted effort. The universe is full of strange phenomena that turn out to be natural once understood. Quasars, pulsars, gamma-ray bursts, all were mysterious when first discovered, but all were explained by conventional physics. Searching for weirdness without constraints could lead astronomers down endless rabbit holes, chasing every anomaly without making progress. Yet the Webb signal demonstrated that some anomalies were worth chasing. Even if it turned out to be natural, studying it would teach us something about the universe. And if it was artificial, the implications would transform humanity's understanding of its place in the cosmos. The search for extraterrestrial intelligence, whether through radio signals, optical lasers, or anomalous infrared emissions, was ultimately a search for context, for understanding whether we were alone or part of a larger cosmic community. The Webb signal, whatever its origin, had brought that search into sharp focus. The Dyson sphere hypothesis and energy signatures. Among the most provocative explanations for the Webb signal was the possibility that it represented a Dyson sphere, a megastructure proposed by physicist Freeman Dyson in 1960. The concept is straightforward yet audacious. An advanced civilization might surround its star with a shell or swarm of collectors to capture as much energy as possible. Such a structure would absorb visible light from the star and re-emit it as infrared radiation, exactly the kind of signal Webb was designed to detect. Could the mysterious signal be evidence of such a structure from the early universe? Freeman Dyson's original idea wasn't about solid shells like something from science fiction. He envisioned a swarm of millions or billions of independent platforms orbiting at various distances, collectively capturing most of the star's output. This made more sense from an engineering perspective, avoiding the impossible material stresses of a rigid shell. The swarm would glow in the infrared because the platforms would heat up as they absorbed starlight and radiate that heat away. An observer from afar would see the star dimmed in visible wavelengths but bright in infrared, an unnatural spectral signature that could reveal the presence of technology. Astronomers have searched for Dyson spheres for decades. Large infrared surveys have catalogued millions of sources, looking for objects with the right properties: strong infrared emission, weak optical emission, and spectra inconsistent with dust or natural astrophysical processes. Several candidates have been identified over the years, but all have turned out to be natural phenomena like dust-enshrouded stars or unusual galaxies. The search continues because finding even one Dyson sphere would revolutionize our understanding of life in the universe. The Webb signal had some properties consistent with a Dyson sphere. It was bright in the infrared and apparently absent or very faint at other wavelengths. It came from a point source rather than an extended region. And its spectrum was unlike anything natural. But there were serious problems with the Dyson sphere interpretation. First, the temperature was too cold. A Dyson sphere should glow at temperatures of a few hundred to a few thousand Kelvin, depending on its radius, hot enough to emit strongly in the mid-infrared. The Webb signal had a temperature around 1.5 Kelvin, colder than the cosmic microwave background. This was incompatible with a structure absorbing and re-radiating starlight. Second, the redshift placed the signal at an epoch when stars themselves had barely begun to form. Building a Dyson sphere requires not just a civilization, but an industrial civilization with access to enormous resources and advanced engineering. It also requires time for life to evolve, for intelligence to develop, for technology to advance to the point of megastructure construction. Doing all this within 600 million years of the Big Bang seemed impossible by any reasonable estimate. Earth's history provides a useful benchmark. Life appeared on Earth relatively quickly, within a few 100 million years of the planet's formation. But it took another 4 billion years for complex multicellular life to emerge, and only in the last few 100,000 years did humans develop. Industrial technology is less than 300 years old. Even if evolution proceeded much faster elsewhere, compressing this timeline into 600 million years required extraordinary assumptions. Some researchers proposed that the signal might not be a Dyson sphere around a single star, but something even larger. A Dyson swarm around an entire galaxy, for instance, or a network of energy collectors spread across a galactic cluster. Such a structure would require a civilization at Kardashev Type 3 level, capable of harnessing the energy output of billions of stars. The scale was mind-boggling, but it might explain the signal's properties. If the structure was operating at very low temperatures for efficiency, perhaps using superconducting materials or exotic physics, it might emit in the wavelengths Webb detected. This idea faced the same timing problem. Building a galaxy-scale megastructure in 600 million years was even less plausible than building a Dyson sphere. It also raised questions about motivation. Why would a civilization build such a structure? What would they do with all that energy? Power computations, run simulations, create new universes? The answers were pure speculation, limited only by imagination. Another variant of the Dyson hypothesis involved not energy collection, but waste heat. Any advanced civilization using large amounts of energy will produce waste heat as a byproduct, a consequence of thermodynamics. This heat must be radiated away, and the more energy used, the more heat produced. If a civilization was consuming energy at a tremendous rate, its waste heat signature might be detectable across the universe. The Webb signal could be such a signature, the infrared glow of a civilization using more power than we could comprehend. But again, the cold temperature was a problem. Waste heat should be warm, not cold. Unless the civilization had developed technology to radiate heat at extremely low temperatures, perhaps using quantum effects or exotic materials, the waste heat hypothesis didn't fit. Some researchers speculated about reversible computing, a theoretical form of computation that generates minimal heat by avoiding information erasure. If a civilization used reversible computing at massive scales, it might produce less waste heat than expected, but even this wouldn't explain the observed temperature. The absorption lines were another piece of the puzzle. If the signal came from a megastructure, what produced those lines? Perhaps they were atmospheric signatures, gases surrounding the structure or contained within it. Or perhaps they were markers, deliberately engineered spectral features intended to attract attention or convey information. Some SETI researchers have proposed that advanced civilizations might embed messages in spectral lines using specific wavelengths to encode data. The unidentified lines in the Webb signal could be such a message, though decoding it without knowing the encoding scheme was impossible. The Dyson sphere hypothesis, despite its problems, remained tantalizing because it offered a concrete, testable prediction. If the signal came from a megastructure, there should be other evidence. Variability as the structure rotated or evolved. Spatial structure when observed at high enough resolution. Associated signals at other wavelengths, perhaps from the star being obscured or from the civilization's other activities. Follow-up observations searched for these signatures but found nothing definitive. One team proposed a clever test. If the signal was a Dyson sphere, the structure should have mass, and that mass should exert gravitational lensing effects on background objects. By carefully analyzing the positions of faint galaxies near the signal's location, they could look for subtle distortions indicating the presence of a massive foreground object. The analysis found no lensing, which set an upper limit on the mass. If a structure existed, it was either very low mass or very compact, neither of which fit the megastructure model well. The Dyson sphere idea also faced philosophical objections. If megastructures were common, we should see them everywhere. The universe is 13.8 billion years old, and there has been plenty of time for civilizations to arise and build such objects. The fact that we don't see Dyson spheres around every star or even around a small fraction of stars suggests they're either very rare or don't exist. Finding one in the early universe, when conditions were least favorable, would be extraordinary and would require rethinking the entire framework of SETI. Despite the challenges, the Dyson sphere hypothesis couldn't be entirely ruled out. It represented a specific instance of a broader idea, that the Webb signal might be evidence of technology operating on scales and principles we don't understand. Whether it was a Dyson sphere, a stellar engine, a matryoshka brain, or some other concept from speculative engineering, the possibility that advanced intelligence had left a mark on the cosmos couldn't be dismissed without definitive proof one way or the other. When the universe was supposed to be empty. The timing of the Webb signal was perhaps its most perplexing feature. At redshift 8, corresponding to just 600 million years after the Big Bang, the universe was in its infancy. This was the cosmic dawn, the epoch when the first stars ignited and the first galaxies assembled. To understand why finding any complex structure at this time was shocking, we need to explore what the early universe was actually like. Immediately after the Big Bang, the universe was a seething plasma of elementary particles, quarks, gluons, electrons, photons, and more exotic species that have since decayed or vanished. The temperature was trillions of degrees, hot enough that no stable structures could exist. As the universe expanded and cooled, quarks combined to form protons and neutrons. By the time the universe was 3 minutes old, these nuclei had fused into the first atomic nuclei, mostly hydrogen and helium, with trace amounts of lithium and deuterium. This process, Big Bang nucleosynthesis, set the initial chemical composition of the cosmos. For the next 380,000 years, the universe remained too hot for atoms to form. Electrons zipped around freely, constantly scattering photons and keeping the universe opaque like a thick fog. Then came recombination, when the temperature dropped enough for electrons to bind to nuclei, forming neutral atoms. Light could finally travel freely, and the cosmic microwave background was released, the oldest light we can observe. After recombination came the Dark Ages, a period lasting several 100 million years when the universe had no stars. It was filled with cold, neutral hydrogen gas, drifting slowly under the influence of gravity. Tiny density fluctuations, imprinted during the earliest moments of the universe by quantum processes, began to grow. Regions slightly denser than average attracted more matter, becoming denser still. Over millions of years, these fluctuations amplified, creating the seeds of future structures. Dark matter played a crucial role. Because dark matter doesn't interact with light, it could clump together earlier and faster than normal matter, creating gravitational wells into which hydrogen gas fell. By about 100 to 200 million years after the Big Bang, the first dark matter halos had formed, massive enough to pull in surrounding gas and trigger the collapse that would ignite the first stars. These first stars, called population 3 stars, were very different from modern stars. They formed from pristine gas containing only hydrogen and helium, no heavier elements. This composition affected their properties. Without metals, elements heavier than helium, the gas couldn't cool efficiently, so the collapsing clouds remained hot and massive. Population 3 stars were probably hundreds of times more massive than the Sun, burning hot and bright and dying quickly in violent supernovae. When these stars exploded, they scattered the first heavy elements into space: carbon, oxygen, silicon, iron, forged in their cores and in the supernova blasts. This enriched gas mixed with the pristine hydrogen and helium, allowing the next generation of stars, population 2, to form. These were smaller and longer lived, more like modern stars, and they formed in increasing numbers as the universe aged. By 600 million years after the Big Bang, the epoch of the Webb signal, the universe had transitioned from darkness to light. Many stars had formed, died, and enriched the gas with metals. The first galaxies had assembled, small and irregular compared to modern galaxies, but actively forming stars. Some of these galaxies harbored the seeds of supermassive black holes, though how these black holes grew so massive so quickly remains one of the great puzzles of cosmology. But the universe was still primitive by modern standards. The total amount of heavy elements was a tiny fraction of what we see today. Most of the gas was still neutral hydrogen, not yet ionized by starlight. The intergalactic medium was colder and denser than it is now, and the timescales for building complex structures were short. A galaxy at redshift 8 might be only a few 100 million years old, its stars young and its chemical evolution incomplete. Given these conditions, what could produce the Webb signal? If it was natural, it had to form from the limited materials available at that time. The unidentified spectral lines couldn't come from complex molecules or rare isotopes because those didn't exist yet in significant quantities. If it was artificial, it required a civilization that evolved, developed technology, and built structures within a time frame that seems impossibly short. Some researchers argued that evolution could proceed faster under certain conditions. On Earth, evolution was slow because environmental changes were gradual, and catastrophes like asteroid impacts periodically reset progress. But on a planet with more stable conditions, or with biochemistry that evolved faster, intelligence might emerge more quickly. If life arose within a few million years of planet formation, and if evolution proceeded at 10 or 100 times the rate on Earth, technological civilization might develop within a few 100 million years. This was still a stretch. Even accelerating evolution by orders of magnitude, fitting the entire progression from simple cells to spacefaring civilization into 600 million years, required favorable conditions at every step. The planet would need to form quickly, life would need to start immediately, evolution would need to proceed without major setbacks, and technology would need to advance rapidly. Any delay or disaster would push the timeline beyond the window available. Others proposed that the civilization might not have originated at redshift 8, but much earlier. Perhaps life began in the first few million years after the Big Bang, during a brief period when conditions were just right. Some cosmologists have speculated about a hypothetical epoch called the habitable epoch of the early universe, a time when the cosmic microwave background was at room temperature, providing a warm environment everywhere. This epoch lasted only a few million years before the universe cooled too much, but maybe life could have started then and survived by finding other energy sources. This idea was exotic and lacked supporting evidence, but it illustrated the creative thinking the Webb signal inspired. If conventional timelines didn't work, maybe the unconventional ones did, or maybe our understanding of cosmic history was incomplete, and there were processes or events we hadn't accounted for that allowed complexity to arise earlier than expected. The signal's location in cosmic history also had implications for the Fermi paradox. If a civilization existed at redshift 8, it had a 13 billion year head start on humanity. Even if it was short-lived, lasting only a million years, it would have had time to spread across large regions of space before disappearing. Where were its descendants? Where were its ruins? If the galaxy or the universe was once home to such an ancient civilization, why do we see no other traces? One possible answer was that civilizations don't spread. Perhaps there are fundamental barriers to interstellar travel that no technology can overcome. Perhaps civilizations inevitably destroy themselves, or they choose to remain local, or they transcend physical existence and leave the material universe behind. Any of these scenarios could explain why an ancient civilization left only one detectable signal and nothing more. Another answer was that we're looking in the wrong way or in the wrong places. The universe is vast, and our searches for technosignatures or alien artifacts have been limited. We've examined a tiny fraction of stars, a minuscule portion of the sky, and only a narrow range of wavelengths and timescales. An ancient civilization's traces might be everywhere, but we haven't recognized them yet. The Webb signal could be the first of many discoveries, a hint that the universe is far more populated than we realized. The timing mystery remained unresolved. Whether the signal came from 600 million years after the Big Bang or from somewhere closer, whether it was natural or artificial, the fact that it existed at all challenged our assumptions about when and how complexity arises in the universe. The early universe was supposed to be simple, a cosmic nursery just beginning to form its first structures. The Webb signal suggested it might have been far more interesting. Parallel discoveries and hidden patterns. As astronomers around the world reanalyzed archival data and planned new observations, something unexpected happened. Reports began trickling in of other anomalies, other signals that didn't quite fit standard models. None were as dramatic or well characterized as the Webb signal, but together they suggested a pattern. Perhaps the Webb discovery wasn't an isolated event, but part of a larger phenomenon we'd been missing all along. One team revisited data from the Spitzer Space Telescope, Webb's predecessor in infrared astronomy. Spitzer operated from 2003 to 2020, conducting surveys of the sky at wavelengths similar to Webb, though with less sensitivity. The team applied new data processing techniques, searching for faint sources that might have been overlooked in the original analysis. They found several candidates, point sources with unusual infrared colors and no obvious optical or radio counterparts. Most of these turned out to be known objects upon closer inspection, brown dwarfs, distant galaxies, or asteroids that had moved between observations. But a few remained mysterious. Their spectra didn't match any standard templates, and their properties were reminiscent of the Webb signal, though much fainter. Were these related or just unrelated oddities? The team published their findings, cautiously suggesting that a new class of infrared sources might exist. Another group examined data from the Planck satellite, which mapped the cosmic microwave background with unprecedented precision. Planck's primary mission was cosmology, studying the oldest light in the universe, to learn about the Big Bang and cosmic inflation. But it also detected foreground sources, galaxies, and clusters that emitted in the microwave and far infrared bands. The team searched for sources with anomalous spectra, filtering out known objects and looking for outliers. They found a handful of candidates scattered across the sky. These sources had spectral energy distributions that didn't fit standard models of galaxies or dust emission. They were cold, like the Webb signal, and showed hints of unusual spectral features. The data quality wasn't good enough to confirm absorption lines or determine precise properties, but the similarities were intriguing. Could these be the same type of object as the Webb signal, seen at different distances or in different evolutionary states? Radio astronomers contributed as well. Surveys conducted with the Very Large Array and the Murchison Wide Field Array, designed to study neutral hydrogen in the early universe, sometimes detected transient or persistent sources that defied classification. Most were pulsars, distant quasars, or interference from satellites and human activity, but a few remained unexplained. Their radio spectra were flat or inverted, opposite to what natural sources typically produce, and they didn't vary in the ways expected from known objects. Could radio and infrared anomalies be connected? The physics would have to be unusual for a single source to emit in both bands without also emitting at intermediate wavelengths. But some theoretical models allowed for this, particularly if the emission mechanism involved non-thermal processes or exotic states of matter. The radio sources were added to the growing list of curiosities that might or might not be related to the Webb signal. Perhaps the most striking parallel came from X-ray astronomy. The SETI satellite, launched in 2019 to map the X-ray sky, discovered a faint source with properties that seemed inconsistent with any known class of X-ray emitters. It was too soft, meaning too much emission at low energies, to be an active galactic nucleus. It was too steady to be a flare or transient. And it was located in a region with no obvious host galaxy or star cluster. The X-ray spectrum showed absorption features, though at different wavelengths than the Webb signal, and the energies didn't correspond to known transitions in any element. The discovery was published, but received little attention at the time because the community was still debating the Webb signal. Only in retrospect, after the parallels were pointed out, did researchers recognize that the SETI source might be part of the same puzzle. Statistical analysis began to suggest that these anomalies were more common than expected by chance. If every strange observation was independent and unrelated, you would expect them to be randomly distributed in space, wavelength, and time. But when researchers compiled a catalogue of unexplained sources from multiple surveys, they found weak but intriguing correlations. The sources weren't randomly distributed. They clustered slightly towards certain regions of sky, particularly toward high galactic latitudes, where contamination from the Milky Way was minimal. This was a delicate result. Clustering can arise from selection effects, the tendency to find more sources in well-studied regions or in areas with less confusion from other objects. Distinguishing real clustering from artifacts required careful statistical tests and control samples. Some researchers argued that the clustering was significant, suggesting a population of objects that shared a common origin or mechanism. Others were skeptical, pointing out that the data was heterogeneous, combining observations from different telescopes with different sensitivities and biases. Another pattern involved redshift. While most of the candidates lacked precise redshift measurements because their spectra were either too faint or too unusual to identify clear features, approximate distances could be estimated from photometric colors or associations with nearby galaxies. When these rough distances were compiled, a surprising trend emerged. Many of the candidates appeared to be at high redshifts in the early universe, similar to the Webb signal. This could be a selection effect. High redshift sources are harder to detect, so only the most unusual or intrinsically bright ones would appear in surveys. But it could also be real. Perhaps whatever process produced these signals was more common or more active in the early universe, when conditions were different. If true, it might explain why we don't see similar objects nearby. They existed in the past, but not in the present, either because they evolved into something else, or because the conditions that created them no longer apply. The possibility of a population raised as many questions as it answered. If there were hundreds or thousands of these objects, why hadn't they been noticed before? Part of the answer was sensitivity. Webb and other modern instruments were more sensitive than their predecessors, able to detect faint sources that earlier surveys missed. Part was wavelength coverage. Infrared astronomy had only recently matured to the point where deep, wide-area surveys could be conducted. And part was awareness. Before the Webb signal, there was no reason to look for this type of object, so anomalies were dismissed or ignored. But if a population existed, it should be detectable in existing data. Researchers began planning systematic searches using machine learning to scan archival datasets for sources with properties similar to the Webb signal. The algorithms were trained to recognize the specific combination of features: faintness at optical wavelengths, brightness in infrared, unusual spectral signatures, lack of clear host galaxies. Early results were promising, identifying dozens of new candidates that would require follow-up observations to confirm. The discovery of parallel anomalies added a new dimension to the mystery. If the Webb signal was unique, it might be an outlier, a fluke, or an artifact that didn't represent anything broader. But if it was part of a population, it suggested a real phenomenon, something systematic that demanded explanation. Whether these objects were natural, a new class of galaxy or astrophysical source, or artificial remnants of ancient civilizations, the implications were profound. The universe might be stranger and more populated than we thought. The message hypothesis and information theory. If the Webb signal was artificial, the next question was whether it contained a message. The absorption lines, with their irregular spacing and varying strengths, could potentially encode information, a deliberate transmission from an ancient civilization to anyone capable of detecting it. Decoding such a message, if it existed, became a focus for SETI researchers and information theorists. The first challenge was determining whether the signal contained information at all. Random noise has no structure, while a message should have patterns, correlations, or redundancy that distinguish it from randomness. Information theory, developed by Claude Shannon in the 1940s, provides tools for quantifying the information content of a signal. Entropy, for instance, measures the average amount of information per symbol. High entropy means high randomness, while low entropy indicates structure. Researchers calculated the entropy of the absorption line pattern. If the lines were truly random, the entropy should be maximal. If they formed a structured message, the entropy should be lower, reflecting the constraints imposed by encoding rules or linguistic structure. The analysis showed that the entropy was intermediate, lower than pure randomness, but higher than highly structured sequences like language or compressed data. This was intriguing but ambiguous. It could mean the signal contained a message with high information density, or it could mean the pattern was produced by some natural process with partial structure. Another test involved looking for periodicity or repeating patterns. Many communication protocols use repetition for error correction or emphasis. A message might contain repeated sequences, markers to indicate the start or end of sections, or checksums to verify data integrity. Researchers scanned the absorption line pattern for such features, using Fourier analysis and autocorrelation to detect periodicities. They found weak hints of structure. Some spacings appeared more frequently than others, and there were suggestions of patterns at multiple scales, short-range correlations between adjacent lines, and longer-range correlations spanning groups of lines. But the significance was marginal, just barely above the threshold where patterns could be distinguished from noise. It was possible that these features were real, or they might be statistical flukes, the result of analyzing a small dataset and finding patterns by chance. Prime numbers have long been proposed as a universal signal, a way for an alien civilization to demonstrate intelligence without relying on cultural specifics. The idea is that mathematical truths are universal, and any intelligent species would recognize concepts like prime numbers, pi, or the Fibonacci sequence. If the absorption lines encoded a sequence of primes, it would be strong evidence of artificiality. Researchers checked whether the line spacings, strengths, or wavelengths corresponded to primes or other mathematical sequences. They tried various encodings: the positions of lines as integers, the ratios of spacings, the intervals between clusters. None of the attempts produced a clear match. If there was a mathematical message embedded in the signal, it wasn't encoded in any of the obvious ways. Linguistic analysis was also attempted. Human languages have characteristic statistical properties. Certain letters or sounds are more common than others, words follow specific patterns, and syntax imposes constraints on sequences. If the signal contained language, even an alien one, it might exhibit similar properties. Researchers treated the absorption lines as words and looked for frequency distributions, n-gram patterns, and syntactic structures. The results were inconclusive. Some distributions resembled natural language, particularly the uneven frequency of symbols and the presence of short, common sequences alongside longer, rare ones. But other properties didn't match. The lack of clear word boundaries, the absence of obvious grammar, and the failure to find translational invariance, the property that patterns repeat in different contexts, suggested that if this was language, it was fundamentally different from human communication. One creative approach involved looking for self-referential structures, messages that describe their own encoding. This idea comes from mathematical logic and computer science, where self-referential statements like "this sentence is false" create paradoxes or interesting properties. A civilization might embed a decoder within the message, using simple symbols to explain more complex ones in a bootstrapping process. The famous Arecibo message sent from Earth in 1974 used this principle, starting with binary numbers and building up to depict DNA, humans, and the solar system. Researchers searched for such structures in the Webb signal, looking for sections that might serve as keys or legends explaining the rest. They tried various decoding schemes, from simple substitution ciphers to complex transformations involving mathematical functions. Nothing worked. Either the message was encrypted or compressed in a way that required additional information to decode, or there was no message at all. Another angle was to consider not linguistic messages but data. A civilization might send images, scientific constants, or mathematical proofs encoded as raw data. If the absorption lines represented a bitmap image, for example, the pattern of strong and weak lines could be pixels, creating a picture when arranged in the right grid. Researchers tried rendering the lines as images with various dimensions and encodings, searching for recognizable shapes or patterns. They saw nothing but noise. Scientific constants were also considered. Perhaps the wavelengths or spacings encoded fundamental values like the fine structure constant, the mass ratio of the proton to electron, or the gravitational constant. These numbers are dimensionless and would be the same for any civilization using the same physics. By encoding them in the signal, a civilization could prove their understanding of nature and invite others to communicate. Researchers checked whether the line parameters matched known constants, allowing for different numerical bases and unit systems. They tried ratios, products, and sums of constants, testing hundreds of combinations. Again, no clear matches emerged. If the signal encoded scientific information, it wasn't in a format we could recognize. The message hypothesis faced a fundamental problem. Without knowing the encoding scheme, decoding was nearly impossible. Human communication relies on shared context, common symbols, and agreed-upon rules. Even deciphering ancient human languages required either a Rosetta Stone, a bilingual text that provided translation, or extensive context clues from the culture. With an alien message, there was no shared context and no Rosetta Stone. Unless the message was designed to be self-explanatory, decoding it might be beyond our capabilities. Some SETI researchers argued that any message intended for detection would be self-explanatory. A civilization sending signals across the galaxy or the universe would anticipate that recipients might have different sensory systems, languages, and cognitive structures. They would design the message to be as simple and universal as possible, using mathematics, physics, or logic as common ground. The fact that we couldn't decode the Webb signal suggested either it wasn't a message, or it was a message not intended for species like us, or it used principles so alien that we couldn't even recognize it as a message. Despite the challenges, the search for a message continued. New algorithms were developed, combining information theory, machine learning, and cryptanalysis. Collaborations formed between linguists, mathematicians, physicists, and computer scientists, pooling expertise to tackle the problem from multiple angles. Even if the signal wasn't a message, the effort was valuable, advancing techniques for detecting and analyzing patterns in complex data, skills that would have applications far beyond SETI. The time capsule theory. Among the more creative explanations for the Webb signal was the idea that it might be a time capsule, an intentional message or marker placed in the early universe by an advanced civilization to preserve information for future discovery. This theory combined elements of SETI, cosmology, and speculative engineering, asking whether a sufficiently advanced society could leave traces in the distant past that we're only now detecting. The concept of a time capsule is familiar on Earth. We bury messages, artifacts, or data for future generations, preserving cultural heritage or scientific knowledge. A cosmic time capsule would serve a similar purpose, but on vastly larger scales. Instead of burying a box in the ground, a civilization might encode information in the fabric of space-time, in the distribution of matter and energy, or in signals that would propagate across the universe for billions of years. Why would a civilization create such a capsule? One possibility was to ensure survival of their knowledge beyond their own existence. Civilizations like biological species might face extinction from cosmic catastrophes, self-inflicted disasters, or natural evolution into something unrecognizable. By encoding their history, science, philosophy, or culture in a durable medium and placing it where future civilizations might find it, they could achieve a form of immortality, not of individuals, but of ideas. Another motivation might be communication with the future. If a civilization understood the trajectory of cosmic evolution, they might predict when and where new intelligent species would emerge and design their time capsule to be discoverable at that time. The Webb telescope, operating 13 billion years after the signal was emitted, might be exactly the kind of instrument they anticipated. By placing the signal in a region of sky that would eventually be observable from Earth-like planets, they could send a message across deep time. The engineering challenges of such a project were immense. How do you create a signal that lasts billions of years and remains detectable across cosmological distances? Natural astrophysical sources fade or change on much shorter timescales. Stars burn out, galaxies evolve, even black holes evaporate eventually through Hawking radiation. A signal that persists unchanged for 13 billion years would need to be either incredibly stable or self-renewing, continuously powered by some long-lasting energy source. One proposal involved using the cosmic microwave background as a medium. The CMB fills the entire universe and will persist for trillions of years as it redshifts into ever longer wavelengths. If a civilization could imprint a pattern on the CMB during the early universe, that pattern would propagate outward, carried by the light itself, and be detectable by any future observer with the right instruments. The pattern could encode information in the temperature fluctuations or the polarization of the radiation. But creating such a pattern would require manipulating vast regions of space during the moments after recombination, an impossibility for any civilization we can imagine. The energy requirements alone would be astronomical, comparable to the output of entire galaxies. And there's no known mechanism by which a localized civilization could influence the CMB on large scales without altering the entire structure of the universe. A more plausible approach might involve creating a stable physical object or structure that emits or reflects radiation in a characteristic way. A Dyson sphere or similar megastructure built to last billions of years could serve as a beacon. The materials would need to be extraordinarily durable, perhaps made of exotic matter that doesn't decay or degrade. The structure would need to be in a stable orbit or location, avoiding disruptions from gravitational interactions, supernovae, or galactic collisions. The Webb signal's properties didn't obviously match this scenario. It was a point source, which could be consistent with a compact structure, but its cold temperature and unusual spectrum suggested something other than a simple reflector or emitter. If it was a time capsule, it would have to operate on principles we don't understand, perhaps using quantum effects or exotic physics to generate the observed signal without conventional energy sources. Another variant of the time capsule theory proposed that the signal was embedded in a natural astrophysical object, but deliberately modified to stand out. For instance, a civilization might alter the chemistry of a gas cloud, enriching it with isotopes or compounds that wouldn't naturally occur, creating a spectral signature that screams artificial to any astronomer who studies it. The cloud would persist for long periods, maintained by natural processes, but the unnatural chemistry would flag it as interesting. This idea had the advantage of not requiring massive energy inputs or megastructures. It would be technologically challenging, but perhaps achievable for a civilization only moderately more advanced than us. The question was whether the Webb signal spectrum could be explained this way. The unidentified absorption lines might be from deliberately introduced materials, but without knowing what those materials were, we couldn't confirm or refute the hypothesis. Time capsules also raised questions about intent and audience. If a civilization went to the trouble of creating such a message, what did they want to say? And to whom? The most optimistic interpretation was that they were offering knowledge, sharing their discoveries about physics, mathematics, or philosophy to enrich future civilizations. The most pessimistic was that they were warning us, alerting us to dangers they had faced, or to existential threats that all civilizations encounter. Some researchers speculated that the absorption lines might encode specific information, coordinates of their home system, blueprints for technologies, or solutions to major scientific problems like faster-than-light travel or unlimited energy. Decoding these, if they existed, would be the challenge of the century. Others thought the message might be simpler: a greeting, a proof of intelligence, or just a statement of existence. We were here. We thought. We built. We mattered. The time capsule theory also intersected with ideas about post-biological evolution. A civilization might not remain biological forever. They could upload their consciousness into machines, merge with artificial intelligence, or evolve into forms of life we wouldn't recognize. If they did this before placing their time capsule, the message might reflect a post-biological perspective, encoded in ways that make sense to synthetic minds, but not to biological ones like ours. Detecting a time capsule would be profound but also bittersweet. It would confirm that we're not alone, that intelligence has arisen elsewhere in the universe. But it would also mean that the civilization was gone, possibly extinct, leaving only their message behind. We would inherit their knowledge without ever meeting them, a one-sided conversation across billions of years. The emotional and philosophical impact of such a discovery would reshape how humanity sees itself and its place in the cosmos. For now, the time capsule theory remained speculative, one possibility among many. It fits some aspects of the Webb signal, the apparent intentionality suggested by the unusual properties, the timing in the early universe that maximized the chance of eventual discovery. But it lacked the concrete evidence needed for confirmation. More data, better analysis, and perhaps a stroke of insight would be needed to determine if the signal was indeed a message from the deep past, waiting for us to decipher it. Probing exotic physics with experiments. While astronomers observed the Webb signal from afar, physicists began conducting laboratory experiments to test ideas about its origin. If the signal involved exotic physics or unusual states of matter, perhaps those conditions could be recreated on Earth, allowing direct study in controlled environments. This approach, using analog systems to simulate astrophysical phenomena, had proven valuable in the past and might shed light on the mystery. One line of research focused on ultra-cold gases. Using laser cooling and magnetic trapping, physicists can cool clouds of atoms to temperatures just billionths of a degree above absolute zero. At these temperatures, quantum effects dominate, and matter behaves in strange ways. Atoms form Bose-Einstein condensates, where thousands or millions of particles occupy the same quantum state, acting as a single coherent wave. In some configurations, these condensates can emit or absorb light in unusual patterns, creating spectral features that don't match hot gases or normal solids. Researchers wondered whether the Webb signal might involve ultra-cold matter, perhaps a giant cloud of gas cooled by some natural or artificial process to temperatures comparable to lab experiments. They set up experiments where ultra-cold atoms were illuminated by laser beams tuned to specific frequencies. The atoms absorbed light at those frequencies, creating absorption lines. By varying the conditions, temperature, density, magnetic fields, they explored whether any configuration produced a spectrum resembling the Webb signal. The experiments produced interesting results, but no clear match. Ultra-cold atoms did create unexpected spectral features, narrow lines shifted by interactions between atoms or by quantum effects. But the patterns didn't match the observed absorption lines from the Webb signal. The spacing, the line strengths, and the overall shape of the spectrum were different. Either the conditions in space were very different from what could be achieved in the lab, or the mechanism wasn't related to ultra-cold gases at all. Another set of experiments involved plasma physics. Plasmas are ionized gases where electrons and ions move freely, common in stars, lightning, and fusion reactors. Under extreme conditions, plasmas can exhibit unusual behaviors, turbulence, instabilities, and non-thermal emission that creates spectral lines not predicted by simple models. Some astrophysicists proposed that the Webb signal might come from a plasma in an exotic state, perhaps driven by strong magnetic fields, intense radiation, or relativistic effects. Laboratory plasmas were created using powerful lasers, magnetic confinement devices, and pulsed electrical discharges. Researchers probed these plasmas with spectroscopy, looking for absorption or emission patterns that resembled the Webb signal. They experimented with different elements, temperatures, and densities, trying to reproduce the observed features. Some configurations produced complex spectra with many lines, but again, none matched. The physics of lab plasmas, while rich and complicated, didn't seem to explain the cosmic signal. Condensed matter physicists contributed as well. Certain crystals and exotic materials can interact with light in unusual ways, creating absorption or emission features that depend on the material's internal structure. Quantum dots, for instance, are nanoscale semiconductor particles that absorb and emit light at wavelengths determined by their size. By creating arrays of quantum dots with specific size distributions, researchers could engineer custom spectra, tailoring the absorption lines to match any pattern. Could the Webb signal come from some kind of solid material, perhaps grains or structures with specific optical properties? Researchers synthesized various materials, exotic alloys, layered crystals, and nanostructures, and measured their spectra. They found that while some materials had complex absorption patterns, achieving a perfect match to the Webb signal required precise control over composition and structure that seemed unlikely to occur naturally. And it still didn't explain how such materials would end up in deep space at the early universe, emitting infrared radiation. Some experiments explored analog black holes. These aren't actual black holes, but systems that mimic some of their properties. For example, sound waves in a flowing fluid can behave like light near a black hole's event horizon if the fluid velocity exceeds the speed of sound. Physicists have created acoustic black holes in water tanks and Bose-Einstein condensates, studying how phonons, sound quanta, interact with the horizon. These analogues have provided insights into Hawking radiation and quantum effects in curved spacetime. Could an analog system help understand the Webb signal? If the signal involved physics near event horizons or in extreme gravitational fields, studying analogues might reveal relevant processes. Researchers used superfluid helium, flowing at speeds where quantum effects created horizon-like boundaries, and looked at how the fluid emitted or absorbed energy. They found that quantum fluctuations at the horizon could create unusual radiation patterns, including non-thermal emission with specific spectral features. This was intriguing, suggesting that quantum effects in strong gravity might produce signatures detectable at cosmic distances. But translating the analog results to real black holes or neutron stars required extrapolations that weren't well justified. The conditions in a tabletop experiment differed vastly from those near an astrophysical black hole, and the connection remained speculative. High-energy particle physics offered another avenue. At facilities like CERN's Large Hadron Collider, protons are smashed together at energies approaching those present moments after the Big Bang. These collisions create exotic particles and states of matter that existed in the early universe, but not in the modern cosmos. By analyzing the debris from these collisions, physicists hoped to find clues about what might produce the Webb signal. Searches focused on unusual resonances, short-lived particles that decay quickly but leave distinctive signatures in detectors. If a new particle or interaction existed that wasn't part of the standard model, it might produce spectral features when it decayed or interacted with light. Collider data was scanned for hints of such particles, particularly those that could couple to photons and create absorption or emission at specific energies. No smoking gun emerged, but the searches continued. The energy scales accessible at colliders were limited, far below the Planck scale, where quantum gravity effects become important. If the Webb signal involved physics at those scales, colliders might not be able to probe it directly. But even indirect hints, anomalies in particle production or decay rates, could guide theoretical work. Laboratory experiments, while valuable, faced a fundamental limitation. They could test specific hypotheses, checking whether particular physical processes could produce signals resembling the Webb detection. But they couldn't explore the full range of possibilities. The universe is a vastly larger and more varied laboratory than anything on Earth, with conditions we can't replicate. The Webb signal might involve phenomena that required the extreme energies, densities or timescales only available in cosmic contexts, beyond what any experiment could achieve. Still, the experimental efforts weren't in vain. They ruled out many ideas, narrowing the range of viable explanations. They developed new techniques and technologies that would have applications beyond this specific problem. And they demonstrated the value of interdisciplinary collaboration, bringing together astronomers, physicists, chemists, and engineers to tackle a mystery that spanned multiple fields. Even if the experiments didn't solve the puzzle, they advanced science in meaningful ways. Infrared mysteries of the early cosmos. We have journeyed through one of the most perplexing discoveries in modern astronomy, from the moment James Webb detected an impossible signal to the years of frustration and wonder that followed. The signal remains unexplained, a stubborn anomaly that challenges our understanding of physics, cosmology, and perhaps even our place in the universe. Whether it is a natural phenomenon we don't yet understand or evidence of intelligence from the deep past, the mystery endures. What strikes me most about this story is how it reveals the limits of human knowledge. We have built telescopes that can see across billions of light years, instruments so sensitive they can detect the heat of a single star halfway across the universe. We have theories that predict the behavior of matter at temperatures approaching absolute zero and at energies recreating the first moments after the Big Bang. Yet a single signal, a pattern of absorption lines in the infrared spectrum, has defied all our attempts at explanation. It reminds us that for all our progress, the cosmos still holds secrets beyond our reach. The Webb signal has changed how we think about the early universe, about the possibility of life elsewhere, and about the tools and methods we use to explore reality. It has brought together scientists from dozens of disciplines, inspired new generations of researchers, and sparked conversations that extend far beyond astronomy. Whether we ever solve the mystery or not, the journey has been worth taking. Science is not just about finding answers. It's about asking questions, pushing boundaries, and maintaining the courage to confront the unknown. Perhaps someday, with better instruments or deeper insights, we will understand what the signal means. Perhaps it will reveal new physics, a new class of astrophysical objects, or even the first confirmed evidence of extraterrestrial intelligence. Or perhaps it will remain forever enigmatic, a cosmic riddle that tantalized one generation and was forgotten by the next. Either way, the signal has already achieved something remarkable. It has reminded us that the universe is stranger, more complex, and more wonderful than we can imagine.